switch idana.
Good afternoon, professors, scholars, and students. Welcome you all for first talk of last session. And we are going to have a professor from Russia. And now I request Professor Thirmalai Vasan, professor of School of Electrical Engineering, to chair this session. Sir, welcome, sir. Sir, Thirmalai, sir. Could you please unmute, sir?
Thank you, sir. Thank you. Thank you for your. Shall we start, sir?
Yeah, yes, sir. Please, sir.
Good afternoon, everyone. On behalf of School of Advanced Sciences, I welcome you all for the 3 days virtual international transdisciplinary conference, VITC-2020.
Sir, Thirmalai, sir.
Yes, sir.
Your voice is breaking a little sometimes.
Okay. Sir, is it fine now?
Yeah, fine, sir. Fine.
Good afternoon, everyone. On behalf of School of Advanced Sciences, I welcome you all for the 3 days virtual international transdisciplinary conference, VITC-2020. It's my pleasure to introduce our speaker for today's session, Professor Valery E. Arkenchev, Professor, Buryat State University, Russia. Professor Valery E. Arkenchev graduated from the Faculty of Physics, Novosibirsk State University, 1982. After graduating the university in 1982 to 1990, he worked at the Institute of Semiconductor Physics in Novosibirsk, Akademogordo. Since 1990, he was invited to work to the Buryat Scientific Center of Russian Academy of Sciences as a scientific researcher. Then he worked as a senior leading researcher at Buryat Scientific Center, Siberian branch of Russian Academy of Sciences. He is a leading specialist of the Buryat State University in theoretical physics and condensed matter physics in the field of nanoelectronics, and he authored and co-authored of 84 scientific papers published in leading Russian and international journals, including 2 teaching books and 3 monographs. Under his leadership, the 6 research grants of the Russian Foundation for Basic Research have been performed during 1999 to 2013. Professor Valery E. Arkenchev's pedagogical activity associated with work in Buryat branch of Novosibirsk State University and the Physics Department of Buryat State University since 1993. In 2002 to 2005, he worked as a head of the group of theoretical physics of the Buryat State University. Since September 2011, he is the professor of the group of space physics, and since September 2012, he is the director of Innovative Educational Center for Space Services. In 2014 to 15, he is the vice rector for scientific work of Buryat State University. And now I invite Professor Valery Arkenchev to deliver his presentation on the title, Control of the Capture on Trips by External Fields. Now I hand over this session to Professor Valery E. Arkenchev.
Okay. Good morning, everybody. First of all, I should like to thank the organizing committee for this possibility to give this report. It's a pleasure for me to speak at this conference. Okay, let's begin. I will go for my presentation. This is my presentation. Can you see everybody? Yes.
Yes, sir, it is visible.
Yes. My presentation is called Control of Capture of Diffusion Particles by External Electric and Magnetic Fields. I want to say about this problem of capturing traps, application of this diffusion equation with reflecting boundaries to this problem. I want to shortly describe effective medium equation and fluctuation mechanism of capture of particles. And then we consider capture of particles under external electric fields and under external magnetic fields. That's for charged particles. And conclusion. Let's begin to discuss this problem. Problem of capture of particles on random traps. It means that traps are situated by random way in the medium. This problem is general problem and is arised in different fields. One is problem we know as continuous time random walks. It means this random walks with memory, with delay on traps. And first it was to explain the problem of transiting currents in semiconductors, in electronics, microelectronics, maybe 30 years old ago. The same problem is arised in when we consider chemical reaction, when we want to control chemical reaction. Another problem is capture on traps in lattice and so on. Now we can add this problem to the capture of particles in the complex system and maybe living system. Okay, and I want to talk about theoretical background of this problem, how we can to describe this problem, and how we need to include external fields in this problem. Okay. I want to remind shortly about Brownian motion or diffusion motion. As everybody knows, when we want to consider to describe Brownian motion, this Brownian motion is widely appeared in different fields, as you know. When we want to describe this Brownian motion, we used usually as fixed flow law for diffusion current. We say this diffusion current is gradient of concentration of particles. As a result, we obtain this diffusion equation, first derivative in time and second derivative in space for concentration of particles dependent on coordinate and time. The solution of this diffusion equation is well known. This is Gaussian form, and the root mean square is proportional time, linear in time. Root mean square displacement. Now this is some facts from the usual Brownian motion. And I want to apply this Brownian motion problem to the problem of capture on traps. We want to consider random distribution of traps in the medium. It means that we consider by random way these traps. Now let's consider, for example, Poisson distribution for random traps, random distribution of traps. It means it is this function of distribution for traps is exponential, is this concentration of traps is length of volume. To simulate, and I want to stress that traps is absolutely absorbed traps. If particles is situated on traps is absorbed and died. So it means that we consider how many particles will be survive after capture on these traps. From a mathematical point of view, we need to consider this problem as use reflectant boundary condition. It means that is this probability of capture in the point of traps is equal 0. It means this particle is absorbed in the next traps, it will be 0 again. So we can say this reflectant boundary condition. And we use the initial condition. No, it means that we have this number of particles which normalize for length of interval. Now I want to consider one-dimensional case, to discuss a one-dimensional case. If we consider effective medium approximation, which was solved by Professor Ryazanov this year, we obtain this as result. Exponential, this is time of diffusion for this, and we have this exponential decay. But this is a result is exactly and is right for only effective medium approximation, or it means that is right for small times. Time is less than time for diffusion on the distance between traps. Then after this, another researchers, Balagurov and Vax, this year 1973, they founded new asymptotical, time asymptotical. It is exponential stretch, exponential law. What does it mean? It means that we have free trap region in asymptotical time will be determined by not all medium, but only this rare free trap region. And this results usually called as fluctuation mechanism of capture. It is right for the big time, when time is more than time of diffusion for distance between traps. Again, this effective medium approximation, it means that we placed traps uniform in the medium. It means so we call this effective medium approximation. If they situated by random way, we have this is another result, free trap region without traps, and this region determines the new temporal asymptotic. And I want to discuss, this is old results which used in this problem for a long time. But now I want to discuss the action of electric fields and magnetic fields for survival probability. It means that we need to solve, from a mathematical point of view, we need to solve diffusion equation in electric field. We need to new term is arised in diffusion equation. This is velocity, and this is first time in space derivative. Usually we call this is drift term. Okay, and we need to solve this diffusion equation in electric field with boundary reflecting condition. I want to explain action of electric field for diffusion motion by qualitative picture. Without electric field, all Brownian motion is uniform. All particles can move in any direction. But if we included electric field, in weak electric field, we have the same uniform motion of the particles. But at strong electric field, it will be moved from uniform to the directed transport along electric field. So when will this transition from isotropic diffusion to directed transport along electric field is arrested? We can estimate this as when drift displacement will be equal diffusion displacement. So the new electric field time is arrived from this estimation. It's a diffusion coefficient divided for square of velocity. So we can expect that this two effective medium approximation and fluctuation mechanism must be changed when time will be more, is compared with this new electric field time. Okay. So we can expect new temporal asymptotic for survival probability of diffusion particle in the medium of with traps in an electric field. Now I want to shortly to discuss or describe scheme of this solution of this problem. We want to find the solution of this problem diffusion equation in electric field in this form. This is eigenfunction in such form to satisfy my refracting boundary condition. When x is equal xi, it will be 0. You remember. And when will be equal xy plus 1, it will be 0 again. So we constructed this eigenfunction. And eigenvalue will have this form. And to find survival probability in electric field, we need to make averaging of our survival probability in I impurities or I traps, and will be average survival probability will be average quantity of this. If we make this procedure as I described above, we obtain in the effective medium approximation the next result: exponential with time divided for time of field. It is remind the result for which will be obtained by Professor Ryazanov in the effective medium approximation with changing characteristic time for new electric field time. More interesting, if we consider another in strong electric field. In strong electric field, we obtain, this is diffusion term from diffusion. This is from distribution of traps, Poisson distribution of traps. And now in electric field, we obtain the new term. This is approximate to Boltzmann distribution in electric field. Velocity multiplied for distance between traps. And in strong electric field, what does it mean? When this is term is more than this is distribution between Poisson distribution for traps. We obtain this term. Means this diffusion term. This is term from electric field, and we must to calculate this integral by Poisson method. If we make by correct way, we obtain the new long-term asymptotic in the strong electric field in the form stretch exponential. You see, it is similar by the results in the mechanism, fluctuation mechanism in the traps of medium, but we obtain the new time again. It means that at small time we have effective medium approximation results as here, but in the strong electric field we have this stretch exponential wave. And I want to show that this asymptotic has universal character for not only one-dimensional case, for two-dimensional case, for three-dimensional case will be the same exponential result. Why? Because as I show some here, this is when we included electric field, it doesn't matter what is dimensionality of the problem. One dimensionality, two dimensionality, three dimensionality, because on the strong electric field, all particles will be moved only one direction along electric field. From this point of view, we obtain the universal result for any dimension, for any dimensional case. Okay. And after this, I want to consider another problem, survival probability in a magnetic field. Before I explain in qualitative manner how electric field acted for diffusion trajectory, but now let's consider action of magnetic field for diffusion trajectory. For example, we have this trajectory without magnetic field. If we included magnetic field, it means that our trajectory will be curved. And due to rotation of electron under magnetic field. So instead, this is trajectory, we have this curved trajectory under magnetic field. Of course, if we have the small magnetic field, we have the same. So action of magnetic field will be less. But in strong magnetic field, we obtain the new, we need to take account the curvature of the diffusion trajectory. Let's estimate velocity in a magnetic field. We can give some estimation as length between traps divided for time, cyclotronic time, time of rotation of particles in magnetic field. So we can estimate it by this cyclotronic frequency multiplied for distance between divided for 2 pi. So if we repeat the same calculation as before, but instead is electric field, we need to use the magnetic field term. We obtain same passing point in the magnetic field will be described by these two terms. First of term, diffusion term, and second is considered with rotation of particle in the magnetic field. And again, calculating by the passing method, we obtain the new result of survival probability in magnetic field in this form, stretch exponential, but with another 1.2 result. And again, I want to say this is results will be universal for motion in the plane perpendicular to the direction of magnetic field. It doesn't matter what is two-dimensional case or three-dimensional case. We have again this asymptotic universal of this. So I want to show the two asymptotics for survival probability of particles in the medium of these traps. So these are results we can apply by the problem of control of capture by external fields. If we included electric field, so we can say by the electric field it's possible to control the rate of interaction of particles with traps or between them due to by directed motion. By the magnetic field, we can control the rate of interaction of particles, but it's possible to, first of all, it's possible to localize the particle in the region, and as a result, it will be to lead to increase the rate of interaction of particles in this region. So, and I want to go to some short conclusion of my report. The action of external electric and magnetic fields for capture of traps was considered. The solution, from mathematical point of view, I obtained the solution of diffusion equation with reflecting boundary condition obtained. And the most of all interesting, the new temporal asymptotic were established, and this asymptotic were dependent on the value of electric and magnetic fields, and these results give the possibility of control of capture on traps problem by fields. These results were published in some publication. This is first is Russian Journal of Experimental Theoretical Physics, Physica A and Chaos. Yes, thank you for your attention.
Thank you, Professor Vellore, for the most interesting presentation. Now the session is open for the participants to ask your questions. You can post your queries in the chat window.
Do you have any question?
So the feedback form link is given in the chat window. I request all the participants to give your feedback.
Okay.
Yeah, I think no more questions, Professor.
So one more question.
Okay.
The applications of these traps where we can apply in the day-to-day life, the application part.
Okay. Sorry, please.
The applications of the traps, you talked about the external electric and the magnetic field. Could you tell us the applications of traps in the applications of the traps? I mean, in addition to the electric magnetic field. Yeah. Some examples, if you could give, still it will be more useful to the audience.
Okay, I want to begin from the maybe from the beginning of my presentation. Yes. I want to remind again where this problem is arised. This problem of capture of particles on traps is arised different fields. First of all, is condensed matter physics in electronics. When we want to explain the problem of transiting currents in semiconductors, this is transiting currents which arise in different electronic devices. And one is the problem is try to explain this problem of transiting currents and how to control these transiting currents. Okay. Second problem, which is control chemical reactions. You know, this is chemical reaction is very important in different fields, and it is very interesting and very important to control this chemical reaction. And so my theoretical approach can show how we can control chemical reaction when this one particle will be moved and other particles will stopped in the medium. So it's possible to consider as model of chemical reactions. Another is capture on traps in lattices and capture on traps in living system, in complex system, and so on. We can consider this is capture on traps in biologic system. For example, capture of drugs in biological system and so on. Okay. One more question.
Tirumali sir, please unmute your mic, sir.
Professor, one more question from Ranjit Matthew Roy. What benefits does this magnetic and electric field trip have over optical tweezers?
What benefit of this fields for application?
Yeah. What benefits does this magnetic and electric field trip have over optical tweezers?
Optical.
Yeah.
Okay. as I understand, I am not sure, but it's possible from my point of view. If we consider in optical physics, we can control, we used, of course, the electric field with considered, we need to introduce another external electric field to control the rate of interaction between particles due to directed motion. Usually we have in optical physics, we have wave, light wave, which arised by the excited light. But if we introduced some traps, we can control the rate of interaction of particles. I don't know how it will be exactly. Okay, it is, I don't know by electric field, but from my point of view, it's maybe more interesting by magnetic field. By magnetic field, we can localize particles in the region, in the considered region. It means that will be due to rotation of particles. If we localize particle in some region, we can increase the rate of interaction of particles. So it means that we can increase the maybe some intensity of reaction of some interaction. No, this is some general, yes, general assumption maybe.
Thank you, Professor. I don't think any more questions, Madhesh or sir. Shall we close this session?
Yeah. Okay. Yes, sir. See. So, on behalf of organizing committee, VITC, I express my sincere thanks to Professor Vellore for his wonderful talk on external fields. And also I thank Professor Thirmalai Vasan for sparing his valuable time to chair this session. Thank you, Professor Vellore, and thank you, Professor Thirmalai Vasan.
Thank you, sir.
Thank you.
Unmute.
Yeah. Professor Vellore, on behalf of the organizing committee, we want to say thank to you. Professor Vellore, thank you so much for joining.
Yes, thank you.
Joining the another session as
Thank you very much. Okay.
on your presentation. And if you are free, I mean, we have Indian time at 5 o'clock, the calligraphy function is there. If you are free, you are most welcome to join us. Indian time.
Okay, thank you. Thank you.
Yeah.
Thank you very much.
Sir, Thirmalai, sir.
Yeah.
Sir, if you wish, you can join. You can continue our sessions. If you wish, you can log out. Sign off.
Thank you.
It is coming, but Dear participants, please note down the validity schedule and be online. So we will start our next session by 12:50. Sorry, 2:50.
Welcome, Professor Subal. Yes, Professor Subal, and welcome. Sir, you need to unmute. Subalan sir, you are muted. Sir, unmute Professor Subal. Co-host, make him co-host. Yeah. Yes. Yeah, you can try. Yeah, it's audible.
So, in the
Wait for speaker. Let's wait for speaker.
Okay. Any other parallel session is there?
No, only for oral presentation we actually had for last 2 days parallel session.
So whether you will join at 3 o'clock?
No, 10 minutes in advance.
Oh.
All the speakers to join, session chairs and the speakers to join 10 minutes in advance. Probably will be joining within 5 to 10 minutes.
Okay. So I'll keep the. Actually, is CV ma?
Yes. Yeah. You would have received PPT.
Actually, I have to take the printout.
No, you can just.
Okay. It's now I can.
Yeah, open it and you can read. That will be displayed.
Sandhyan?
Yes,
The-
Professor.
Actually, my screen
Yes, yes.
I can't see my screen.
No, you are made as a co-host. You can see.
Sir, otherwise we will share the PDF file, sir. Sorry, PPT
Okay.
file. You can see that, and you can.
Sir, Nakiran has come. Please make him co-host. Professor Nakiran has joined.
Okay.
Please make him co-host. Sir. Yeah. Just a minute. Okay.
I think.
Sir, can you see the slide, sir?
Yes.
So, Valan, this is from your screen?
Yes. No, actually, I have not shared.
Oh, okay.
No, I'm having the PDF.
Okay.
I think I have to see that screen.
Yeah. You can open. Sir,
Whether we can start.
You can unmute. You have been made co-host.
Okay, can you hear me now?
Yes.
Yes.
Thank you for joining us.
Yeah. Give me a minute.
Just 2 to 3 minutes, we will start.
Yeah, I mean, we have to start at the time, right? Because scheduled time is 10:30 local UK time.
Yes.
Some audience may be coming exactly at that time, right?
Yes, sir.
They want to join, they come only at that time. So we should not start. Yeah.
Yes, we will wait for.
Because even I have given the link to my PhD students, so they might join. So they will join.
Yeah.
Good afternoon, sir.
Yeah, hi, good afternoon. எப்படி இருக்கீங்க?
Good morning, Nikhil.
எப்படி இருக்கீங்க? எல்லாம் இந்த டைம்ல அங்க இருந்திருக்கணும்.
Yes.
கனெக்ட் பண்ண வேண்டியதாயிடுச்சு கடைசியில. கோவிட் வந்து என்னென்னமோ பண்ணி விட்டுச்சு. The audience for this meeting it has been sent to all the VIT students?
No, for registered participants only. MSc students, they attend first year MSc and second year MSc.
Okay.
And we have, in addition to that, we have registered participants across the globe.
Okay. So that means what? Everybody will have their own login password to log in?
Yeah. We have shared actually login credentials.
Okay.
ID and passcode.
So my ID and passcode can be used by my students, right? They can join, right?
Yeah.
Okay. If they cannot join, then I have to tell them that they cannot join.
Yeah, they can attend.
They can, right?
Yes, they can.
Thank you.
So the ID and password will be same for all.
Okay, so it's shared for all the audience.
Yeah, no problem.
And then the organizer will open up the as a host for only for the speaker, right? For the time of the talk.
Yes. Yeah, the only difference is you are now co-host and the others will be participants.
Okay. Because at our university, we don't use the Zoom, we use the MS Teams. They still have.
No, we have both. We use MS Teams for our classes and other things.
Okay.
This Zoom is only for conference.
Okay. Because our university still stay with the security reason that they don't.
Yes.
Even anybody tells that now the security is okay, they don't want to use that.
That's true. And this what we have is only for a month. That's Zoom.
This is the professional edition, right? You have to pay money.
Fine. Let it be.
So the previous talk completed a bit early, or there was no talk earlier before this?
Yes, sir. It was a bit early.
Okay.
That is why mostly we occupied completely, even though we give a 15 minutes gap. Mostly it is question hours extended and introduction of speakers. So it is completely occupied in general.
It goes start to end for the.
Yeah.
Not easy to organize interdisciplinary conference. I remember I attended one in Florida, in Tampa, and they scheduled my talk on a Friday evening.
Okay.
And then also that weekend was a long weekend because of July 4th or something. They have the Independence Day.
Okay, sir. I'm sorry. We are also put like the same manner.
What happened? You cannot believe. I gave a talk for your invited talk only for the chairperson.
Oh.
It is Florida, and everybody went to all the NASA and I think it's in Orlando, not the Tampa. Other conference was in Tampa. Orlando. They went to Disney World and everybody gone. So I told the chairperson, okay, we can just get rid of this talk. I mean, I can also go to NASA or something. But that guy said, no, I want to listen to your talk.
Already 100 people are there in the row, sir.
No, I'm not worried. I'm saying that I'm ready to even talk to for myself. I'm okay.
No. People are still joining there.
That was a very good experience for me. So, okay, and it was a one-to-one talk in a conference.
Speaker, introduce myself.
Dr. Nakiran sir, Dr. Vellore from Russia is waiting there to listen to your speech. He was the previous speaker.
Okay.
He is from Buriyat State University.
Okay.
Yeah, it's also on the.
Oh, Professor Sivabalan? Okay, okay.
Yeah.
Okay, audience. Now let's start our second talk of this session. Here I request Professor Sivabalan, Dean of School of Electrical Engineering, to chair this session. Over to Sivabalan, sir.
Thank you, Professor Madheshwaran. Thank you for giving this opportunity to act as a chair for this session. First, I welcome Dr. Nakiran, Sir, University of Aberdeen, UK. And I welcome all the participants and the professors who are in to attend this session. So it's my privilege to introduce Dr. Nakiran. He got his BE in Electronics and Communication Engineering, CIT, Bardere University. He obtained his PhD and MTech from Anna University, and he is a postdoc fellow from 98 to 2005 in India, France, and Hong Kong. And he has a project, around 22 project he has completed, and specifically the Brings Trust Fund Research Travel Fellowship he had with the DO India, and the Professor International Travel Fellowship with the Royal Society, and other honors are Fellow of IIT, and is a senior member of OSA, Neural Foundation newly appointed Lecture Award, Hong Kong Polytechnic University Postdoctoral Fellowship. So he has also had a CSAR, SRF and JRF fellowship during his stay in India. And he has done a lot of consultancy work, and is specifically his research area focus on fiber optics, specifically the nonlinear fiber optics. So now I think to his credit is having more than 200 publication in highly reputed journal. Now I request Dr. Nakiran to give his speech, and followed by we can have a discussion on this. Thank you. Over to Dr. Nakiran.
Yeah, thank you very much, Sivabalan, and thanks for everyone who joined here. It's a pleasure been giving this talk. I've been invited by VIT. Actually, I mean, I'm a visiting professor there. I visit during the summertime. This time I supposed to be there, but unfortunately, because of the COVID situation around the world, we are all attending a meeting and listening to each other's talk. Okay, I mean, my talk is the interdisciplinary conference, so I'm planning to give the talk so that the most of the audience can get some information about some optics, and they can use it for their further thing, whatever they want to do. Either they want to do some higher studies, or they want to use it for some research, or even for their own research work. Nothing to do to optics, but still we can learn and come with the fantastic ideas if you know about everything is happening only because of we can see things. So I'm going to present the talk in such a way that it can give a good idea that how the optics is very useful in different applications and used for different various things. Okay, so let me, all of you guys can see my screen?
Yes, 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 Nance.
Yes.
Screen, right?
Yes.
We can put it in full screen.
Let me see. Is it in full screen now?
No, I think.
sharing is paused to bring the. Okay, it's not going to. It is not. You're not seeing the screen, right?
Yeah, we
No,
are
we are
seeing, sir,
seeing
but
the
not
screen.
full screen.
It's not in full screen mode, but we are
Oh.
seeing the.
Okay, so whatever the screen you see, that is the.
Yes.
I have a
Yes.
full screen here. Okay, so
Fine.
yeah, so just keep it like that, because I don't think I can do anything further, because for me it is a full screen. So it is because of the PDF or something. But it is legible, right? You can see what is written on my screen, right?
Yes.
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 Okay.
Yes.
Okay,
Yes.
I will go ahead with that. Okay, I mean, as I said, I have a very strong collaboration, not only as a visiting professor with the research work, and also many of my collaborators in VIT, including the chairperson, have connection through Anna University, where we had at least our master's or PhD. We have either done the lasers and electro-optical engineering, intech there, or a PhD there, and something like that. So I have plenty of people to name in VIT. So I have a big list. So I just don't spend time on naming everybody. But this work is in collaboration with, Sendil Nathan, Sivabalan, and Ramesh Babu at VIT. So let's. I mean, where I am from. Actually, now I am at the University of Aberdeen, and let's go to the first slide. I put the title as the light. I give a name as God of Information and Intelligence. Simply, the word I used as a God, because whatever we know, most of the things are known through our first sensor, which is the vision. So we see things. So we look at things. Even if you want to do anything, we have to look at things. So that itself is starts with there is a source.
Excuse me, Professor.
Yeah.
Slide is not moving, sir.
Yes.
You cannot see my slide now.
We see first slide.
Next slide.
First page. Only the first page.
Yeah,
Yeah, it's
fine.
clear now.
Okay. Okay. So the light is the God of information and intelligence. I put it as information and intelligence in the sense that all the information we gather and we see, we look, and even we read things, even this conference, everything is happening because of light. And when we say light, we have all the three pieces of the whole system, which is starting with the source of the light, and then the medium where the light is getting communicated, and then the end one is our detector, that is our eyes. Okay, it's actually the natural camera. I think 99.99% of the living beings have the eyes. Okay, I mean, there are still some 0.01% of species, they don't have eyes. And there is a separate research on that, even how the evolution of the species started having the eyes, and what is the connection of the retina, the iris, rods, and everything. Based on the eyes, and is a separate research altogether. Okay, so eyes itself is a beautiful detector, natural detector, which is available for us to tell us a lot of. So here I put it as information. That means the light is carrying the information and helping us to look at it, to know about it, and understand it, and all those things. And the intelligence, I put it in the sense that what the light is doing to us from the source to the detector, we can learn a lot of things. We can gain some knowledge. We can get, we will become more intelligent if you process it in a proper way. And everything is happening because of that. So that's why I give the title for the light as the God of Information and Intelligence. So the main source of light for us is the sun. So, I mean, I wish to give the first Tirukural. அகர முதல எழுத்தெல்லாம் ஆதி பகலவன் முதற்றே உலகு. So I stress the word Pagalan. Okay, so that is not Bhagavan, it is Pagalan. That is what Thiruvallur actually wrote it. So what he said as the very first stanza in the Tirukural is, like every language starts with the letter A, so everything starts with the first and only light source, which is the sun. So Pagalan is in Tamil is the sun. So the source of light is from the sun, and everything is happening because of that. even before the Earth, the planet, and all the solar system all started, it all came from sun. We all came from the sun. So even if you want to say the real God, what we can see in our life is sun. We all came from sun. So sun created us, and we are still getting all the things from the sun. So sun gives us our planet at the right place, and the source of light is reaching us, and we have the beautiful atmosphere which is covering us and make it possible for the current Earth with all the species and the living condition, including the COVID corona condition. Everything is only through the sun. And then the source as a sun, and all the way the light electromagnetic wave which is traveling, it's gone through all the processes and everything as whatever the medium can give to the light signal can be affected by or influenced by the medium. And then finally, the detector is whatever is receiving the light is a detector. Okay, so I said eyes is a detector, fine, because we can see that. But anything which is influenced or affected by the light will have an effect. Okay, so other planets are in different distance from the sun, so they are influenced in a different way, and they have their own way of how they are and what is there and everything. And we try to see what is happening in other planets also. So everything is caused because of the electromagnetic waves from the source reaching a detector, and what the detector has affected because of that. So that is the thing. And even take, as I explained, all the optical system and the sensing, basically it starts from very natural phenomena. Okay, so I just used this picture. Hope it is good enough in the size. You guys can see that. So the source of light is reaching the Earth, and you see we know the axis of the Earth is in the spinning axis is tilted, I think 22.5 degree, like this way. And then when it goes through a elliptical circle, this elliptical path will give you this part of the pole is closer to the sun, and the other side is in the other way. And then when it comes to the other side, it will be in the opposite way. So that is why we have the seasons, and everything is happening. So everything is happening. If you consider this as the detector and this is the source, so the light is traveling in the medium, and everything is happening here. And also, if you see that the light seen by all the species or this half of the Earth planet, we can consider that there is a periodic cycle of the sun is rising, and then there is a full day cycle. That day is completed. We have seen the full light of the spin of the Earth, and then the sun is setting, and then again the night falls, and then again the next day starts. So you can see that even the digital signal waveform is, actually it is a very macro scale in the time, because it is actually consists of from midpoint here to midpoint here, it is the one full day, including the day and night. Okay, so all this information actually for humans to understand that the Earth is not flat, and actually is rotating the sun, everything took long time for us to understand. But basically, if we started putting a graph like that, the light is increasing, and then it is staying flat for a certain period of time, and then falling down, and the night is staying for a certain period, and then again the sun is rising. We could have understood everything very long back, even before Galileo invented the telescope in 1600. Even before that, but the problem was, even we don't know how to measure the time. The quantify the time was a bigger problem. And once we started making that, slowly we started learning throughout the year. On any given day, the time duration of the day of the cycle, that part is not a constant. That is also changing. And we cannot even explain why those things are happening. Now, after we understood everything, it's very easy to understand, oh, this is why it is, because it is moving in an elliptical cycle, and then it is also have a tilt, and then that's why you have different seasons and a longer day, shorter day period, and all those periodic cycles and everything is clearly understood now. But before we understood everything, it was a bigger problem. So the main point I'm trying to say here is, it is two-way path here. Like, you first explain all the solar system and the source of the light coming from the sun. That is why the planet is like this. That is why we have day and light and everything. You can explain from the solar system and all the planetary motions and everything. Or if you start observing and measuring the light through a detector, like even just we see that there is a daylight, and then it is going to be night, and then there is going to be a cycle of that. from the detection of the light, how we see things, we can explain how the solar system can be. So you can see the connection between that, the information and the intelligence, they are connected both ways. It's not that we cannot say that this is happening because of that, or because of that this is happening. So they are interconnected. And also now it looks like it is very redundant, but actually it is not redundant. The day and night cycle, it has to repeat. It has to go through the same way. It should not change. If it change, then we can't exist. The planet cannot exist. So even though it looks like a redundant information or intelligence, we need that to keep continuing. So that is very, very important. So with that as a very basic thing, I like to say, what humans have done that they have developed many sources, particularly the broad source, the light from the sun. Slowly, when the electricity and the bulb was invented by Edison, and slowly the source of light has come from a broad band of light, and then slowly the broadband has become a narrow band, like sodium vapor lamp. It gives only 2 spectral lines. So the information inside the light has properties. There are a lot of properties. The light intensity, the light is very strong, or it is a weak light, or no light, or even if there is light, whether the light is continuous, that means you switch on a source, that means the sun is a continuous light. That is always the light from the sun is keep coming. But we as a detector, we see it as a earth is spinning. It is one half of the day, given day, we see that, and the other we don't see that. If you don't see that, that means that light in the sun is not switched off. The source is still sending the light to us, but the detector, that is our vision, and the off of the earth has turned. That is why we have the nightfall and we don't see the sun. But the source of the sun is a continuous light. But some sources we need not need to be continuous. For example, our lamp, we want to switch on and switch off after some time, so we can switch on and switch off. When we have this kind of property, that time scale of the light given out by the source can be controlled, can be switched on and switched off, that will help us to say that, okay, for this time of duration, I'm going to tell you this is my information. Like good olden days, we used the fire as the information to be communicated from long distance. So the people from one place, they climb to the top of the tree or climb to the top of the mountain, and then they lit up the light to show that, okay, this is the information. So they may have a different time period, or like the light is on for 2 times or 3 times or something like that. Slowly we started using the on and off switching of the light as the information or the intelligence that can be passed on to somebody who can see that using the detector, which is our eyes. Then slowly, if you see that when the Morse code came into existence, the katkada and everything, what we started using between the ships, the communication, or from the shore to the ship, they used the light, the torch light. They can use the cutoff of the light using the Morse code can be used as the source information. And slowly, when the electronics developed very fast, we can easily electronically switch on and off the source of the light. That can go now to the even very small 10 power minus 12 or 10 power minus 15 up to femtosecond range we can easily achieve now. So the bit rate of communication becomes so fast. So that is how the world has developed very fast after the electronics, and how we can switch on and off different system. The same reason why the digital computers all evolved to this level. Both the communication using the light and other electromagnetic signal, or even the sensing, become very, very vast, and we have the ability to look into things very minute. So the question is, when we have not invented any of this, the source of light was only the sun. It was always continuous. So we had a limitation on that. But now we developed the technology, and we have the know-how how to develop different sources, and it can give the light out with a different time scale. Okay, you can switch on and switch off, and how periodically you want to do that can happen. And also the light has other properties, like whether it need to have a low intensity or high intensity, that can be controlled. And the light, as it is in the part of the electromagnetic spectrum, it has different frequency and wavelength and everything. That also can be switched, and even within the given particular frequency or wavelength, how much broad I want it, the signal, because those things will be useful to detect something or to communicate something. All these things can be controlled now. And as we do that, the medium also, depending on that, the air or the glass or whichever is transparent to propagate the light, it will be influenced by that property because of the time scale of the light, or because of the intensity of the light, or because of the wavelength or the bandwidth. The medium also behave it in a different way, absorb fluorescence and all the spectroscopy and even the loss and everything is based on all this property. And at the very end, the detector is the big question mark. Now the question is, if you know how to produce such a light in a short duration or broader duration or different height level or in the frequency domain, whether it is a short, the broadband or a short band or what wavelength it is sitting there and everything. Now, after it is passed on to the medium, either it is for communication or for sensing something, and at the very end, do we have the detector which can complete the job of, okay, we started with this source of light with this much property of the time and the height and the frequency or the width or something, the bandwidth, and the medium is going to influence what is happening within the medium, and finally the detector is going to detect it, and that will be confirmed as a electrical signal, and that electrical signal analysis will tell us what happened to our light. So let's say I want to start with a communication of the light. I want to send my logical bits ones and zeros that will be communicated, and I want the ones and zeros exactly at the same place in time and received at the detector as ones and zeros in the same time location. That means everything is happening very beautifully, and I will receive the information without any distortion or loss of the.
Next, the slide actually now it is in second slide.
Yeah, maybe I will.
Okay.
Yeah, okay, I will, because I keep talking and forgot to move it down. So the information we have, actually I could go over here to tell that. Okay, so this is the thing I was talking about. So the signal is going to, the light signal is going to feel the medium, and the medium is going to affect the light signal. Even if you take the very basic property, we call that as the medium property as susceptibility. The susceptibility will, through that we can calculate the refractive index. Obviously, the refractive index will come from the permittivity and the permeability of the medium. And once we know that, the refractive index, actually, all of us will know what is refractive index. If somebody asks us what is the refractive index of glass, we say that it is 1.5. Even at the school physics, we learned that. But the refractive index is actually a complex quantity. So the imaginary part will give rise to the loss to the system, and the real part, which we call that as the normal refractive index, which is the thing which will give rise to the dispersion when it is a function of frequency, or it will give rise to the nonlinear effects. There are plenty of nonlinear effects. I'm not going into the details of that, but the refractive index as a function of intensity will give rise to that. So once we have all these effects, the loss, the linear effect, and the nonlinear effect, the medium is getting influenced because of the type of the source signal starting from the source. Finally, the detector has to detect that. So all these loss effect or the dispersion linear effects or the nonlinear effects, they are all problematic effects for our communication of the signal, because we want our ones and zeros in the bit position, and also whatever the ones and zeros, we want them to be received, and the detector has to detect that exactly as it is sent by the transmitter, because the transmitter is trying to tell something to us, that is want to communicate something to the end detector, the receiver. So the medium should not change any of the information. The information, whatever, like what I talk, has to be taken by the microphone and then communicated, and at the end, when you listen to that, whatever I talk has to be received there as such. Okay, if the medium is going to affect this and influence this, we are in trouble. So that is the bigger problem with the communication. So most of the communication studies is about how to increase the bit rate, the bandwidth, or even how to make it error free. Okay, whatever we see, like it has to be very fast. Like when you watch a video in a screen, let's say it start buffering, we don't like it because the bandwidth or the the rate at which the data is communicated is not good enough for the data to receive from the transmitter to the receiver, and we are just waiting for the data to be received. Until then, it will be just buffering. Okay, we don't want that. Even when the signal comes, it is not exactly showing me, or I'm listening exactly in the audio what is being transmitted from the transmitter side. That also I don't want. So all those things has to be completely processed, and then the system, the communication system, has to be designed in such a way that we don't face that kind of problem through the communication process. Okay, that is the one side of the optical systems. The other side is the sensor. Optical sensor is actually the other end, which we are using it in most of the places nowadays because of a lot of advantages we have. But the beauty is, whatever we just said as this loss, dispersion, all the nonlinear effect and the medium influence and everything, that is a bad thing for the communication of the signal. But for the sensor, let's say we want to sense something that is, which is in the medium, any of these properties are affected by the sensor, the sensing medium system, the light is affected by this, that is good, because that will tell us how much the amount I'm looking for. Let's say somebody is sending a light signal from some place and it is very cloudy, then the light is very diffused and I cannot see it properly. Immediately we sense it through the eye, and we immediately the brain process and say, oh, there is mist there, there is cloud there, there is fog there. That itself is telling us there is a sensing thing already happened. So the optical sensor is basically working on that sense. So the light signal from the source, and then the medium is the sensor, what you want to measure from that, and that is the light signal will take that information and tell it to the detector. Then we can understand, oh, this is what is happening. Like even, I mean, I remember my father, he will tell that, okay, when we switch on the gas stove, by the color of the light itself, if it is in the blue color flame, then he says it is at the very high temperature, the gas burner is working very properly, it is good to have the cooking like that. But if it becomes yellow to a, blue to a yellow light, the flame become a blue yellow light, that means there is some problem with the burner holes or the flow of the gas or something. Then we have to stop the cooker, the stove itself, and we need to clean it and everything. We have to make it look like a blue flame, because the yellow flame is actually waste of energy, efficiency is less. The temperature of the yellow flame is very low compared to the, 1200 to 1800 degrees centigrade or something like that. So the color of the light itself, the human can sense and say something about that. Even the star, when we see a star and we receive it, the light, if you make it in the spectroscopy, the wavelength of the light received from the star, we can say that what kind of elements are there in the particular thing. Like when you light up the firecrackers, if you remember during the Diwali time or whenever you have a firecrackers, you see different kind of colors of light are coming out. Why the colors are different? Because different elements, magnesium will burn it in a green color, or the copper will be in a blue color, or sulfur will be in the yellow color, like that. So lot of information can be sensed through the light. So the light is going to tell us a lot of things. Now again, the question mark is what you want to sense. Do you have the proper source of the light that can be sent through the medium, sense it, and then the detector has the property efficient enough to detect it and tell and analyze as, okay, this is what is happening, or this is what the constituent is, or this is the whole thing and everything. So that is the whole idea. Okay. So at that point, let me give a brief introduction about the electromagnetic spectrum. Then quickly I can go to the main topic, the sensor, the photonic crystal fiber sensors. Okay. So here is the spectrum, which starts from a very low frequency to the high frequency, but the wavelength will be the very high wavelength, large wavelength to a small wavelength. So here we can see the radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays, and then cosmic rays, which comes out of the earth. We don't need to worry about that. So these sources of all the electromagnetic spectrum we receive from the sun, obviously. And also we have sources now, the humans know how to make it and how to tailor make it in such a way that for this much duration I want, this is the wavelength I want, and this is the intensity I want, everything can be done. So the beauty here is these are all electromagnetic wave spectrum. The source of these things comes from, for example, the radio waves. they come from antenna. That is what the, so the oscillator and everything, the electrical current is the source for this antennas. So the current, electricity and electric potential, everything is happening with the material which has the electrons in the conduction band. And then when you go to the next level, which is the microwave, the sources are, I mean, normally the microwave is the dish antenna where we use it for our satellite communication, or the microwave which use it for our the mobile phone and everything. So they are all dish antenna or the rod or different kind of antennas are available. Again, we are still sitting in the conduction band. And when you go to the infrared and somewhat near to the connection between the wavelength that is in between the infrared and microwave, molecular vibrations and rotations, those energies are the one which is giving, that is the source for that. For example, the water molecule, which has the oxygen and the 2 hydrogen, the vibrational energy of the 2 hydrogen with the fixed oxygen, that is a particular microwave wavelength. That is what we use in our microwave oven. Because the microwave oven, when you keep the food, which is having some kind of moisture or the water, the microwave of that particular wavelength will be absorbed by the water, and the water, the 2 hydrogen atoms will start vibrating. So that vibration, when the food is around that, that is going to hit the food. So you keep on hitting something, you feel the heat. So that is how the microwave is heat up our the food and everything. So all these sources are coming from the molecules. And then when it comes to the visible region and the ultraviolet and some part of the, I mean, all these things are in the valence band. So the jumping of the electrons to the higher energy level, that can happen only if the energy of 1 photon is given to that, then it jumps to the higher level. When it is already in the higher level, energy level, when it drops down, then 1 photon is coming down. So that is the source of the light. So slowly in the atomic structure, we moved from the conduction band to the valence band to the inner electrons and everything. And then the X-ray also, the inner electrons. We need to ionize the atom. We have to take out the valence electrons. And then inside that, the inner electron going up and down will have very high energy. That energy comes out as a X-rays. And then the gamma rays comes from the nucleus. That is alpha particle, beta particle, and the gamma particle in the radioactivity. That is where from the nucleus, the energy comes out as electromagnetic radiation. That is what the gamma rays. So all the material in the universe are connected to the electromagnetic wave from the conduction band all the way to the nucleus. So that is how the humans started processing everything, and they made the different kind of oscillators for different wavelengths. And that is the source of the different electromagnetic wave signals. So the laser source is one of the beautiful source we have at this part. From the infrared to visible to the ultraviolet, we can make use of the laser source to do that job. Okay. Now the size and the matter size also is very important. We have checked into the light source, and then the duration of the light source and the intensity and other properties as well. Then we looked into how they are produced because of the conduction band activity or the valence band activity or the inner electrons activity or the nucleus activity, different source of electromagnetic radiation comes out. But now in the medium, when it is interacting with something like the air or the glass or the metal or whatever the material, the size of the material also is very, very, very important. For example, I mean, all of us knows, in the last decade or so, the nanotechnology has come up in a huge scale in a different way, because the same material, when it goes to a nanoscale, it is behaving differently. So when it starts behaving differently, it has totally a different properties. For example, if you take a gold material, normally the ornament gold, everything will be glittering in yellow color. But if you start cutting the gold into very, 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 very thin film, and if you go to the nano level, the gold won't look like a yellow color anymore. It won't glitter anymore. It will become a green color material. Okay, because how the light interact with because why the gold is looking yellow or glittering, because it is a bulk material and the light comes and reflected because of the lattice structure of the gold in a bulk material that decides the color of the material. Okay, but when it goes to the smaller nano level scale, then the lattice structure and everything is in the nano level is different from the bulk level. Then the light interacting to that and the light given out by the material will be different. Same thing with the properties as well. So the permittivity change, the permeability change, both will make it the property, everything behaving it in a different way. like even if you take our the Siddha medicine, okay, we make the metal into small powder, small pieces, like we call that in Sanskrit as paspam, like dust particle. Okay, so it's a nanoparticles. When it goes to that level, then the same metal which is toxic can become a medicine. So that is what the Siddha medicine is basically based on. Now we call that as a nanotechnology, but somehow we invented that very long time back. So the medium or the material size also plays a very important role. So that is the one of the main property we are going to see in our photonic crystal fiber. So here I take two examples. One is a butterfly which has a blue color, and there is another naturally available material, the fruit, the apple. This gives a red color to us. We immediately, by the color of it, we say it is in red color, but this is in yellow color. What is the difference between the two colors? This red color is because of the pigment that is of the material which is made of this whole apple skin, that gives the pigmentation color is red. Okay, it's the material color. But here it is not the material color. What is happening with the butterfly? Like, let me go to the next slide. If you go to the electron microscope and see the structure, actually, they are actually in grayscale, okay, black and white material, but they have the natural photonic crystal level. So if you take it in the micron level, then we can see the size between the ups and downs and the holes and everything. They are in the wavelength range of the light of that particular color. Then they will decide what light can go through this hole and what light cannot go through this. So it becomes a light filter because of the structural way it is formed. So the different beautiful color of the peacock feather or the different colors of the different butterflies, they are not real pigment. They by themselves, they don't have any color. So the light has all the wavelength, the sunlight, and then when it passes through some microstructure like this, and the nature of the structure and how the pattern is, thus decide how the color of the butterfly is or the peacock feather colors and everything. So these are all natural photonic crystals that are available. Then once we know about this, then why can't we do that as a material also? That is where the whole thing started as our the microstructure. So the fiber, let's say we design an hexagonal structure like that, and the solid portion is all the glass or the plastic which is transparent, and the black dots you see, they are all holes. Okay, so this is the cross section. So this is the fiber, very long fiber, but we are seeing the cross section. So this is in the micron scale. This is due to the SEM image, scanning electron microscope image. So this kind of fiber, when they come into contact with some external material, like for example glucose or some other thing, then the light which is actually captured inside the core, which is traveling only inside, that can be influenced by that. That is how the sensor is designed using the microstructure also. So now we are going to make use of the property of the signal which is given by the source, and then the material property, which is the sensing medium, we want to sense something, and then finally the detector. So this can be shown up like this is the source, and then we take a fiber to connect the light to the microstructured fiber, which we call that as a photonic crystal fiber, that can have different structure. So we can design the structure in different ways so that we have a place to keep our analyte. The analyte is actually the sensing thing. For example, it could be our blood, or it could be our urine, or it could be some gas material. We can keep a chamber and then we can pass on a gas or something like that. So whatever the material and the property and the dielectric properties of that one will influence the signal that is passed in the core of this particular microstructured fiber. And at the very end, we take it again with a normal fiber, and then we make it to a detector. Through an oscilloscope or a intensity detector, we can just try to analyze. I started with a source of light with this much properties. I know what is the time duration, what is the intensity of the signal, and also what is the wavelength and the bandwidth, everything. Pass through this medium, which is making the environment which we want to sense, that is influencing the light, and then that light property, either the time duration get changed, or the height can get altered because of the loss, or the wavelength can change, or it can be having a broader or shorter bandwidth or something. that can be finally measured, and that will tell us what are all the materials and what I want to sense. For example, if you take the blood, depending on how much glucose content with the blood, the refractive index will be different. Okay, high glucose content will make the blood with some refractive index. Low glucose content will make it as a low refractive index. Even very small molecular amount of variation can also change the refractive index very easily. And this microstructure of the cross section of the fiber can be designed in such a way that we can place the blood or whatever the thing we want to analyze with, and then the light signal get affected because of that, and we can measure with that. So the idea is, this is the common general idea I have given to all of you. But in the current research, what are all the things happening? Even I said the thin film of some metals like silver or gold, and they have their own way of behaving with the light. We can also coat the silver or the gold in there, and it can become, okay, I can go directly to the, here. So you see, this is the full fiber. Actually, we polished one side, so it will look like a D shape, and we make it as a wedge shape, and we can have a coating of the yellow color, small yellow color, that is our gold layer. And we can keep the whatever the sensing analyte on that. The refractive index combination of the analyte and the gold material or the silver material, that will decide what should happen to the signal which is passed in the middle of this microstructured fiber. Okay, so that is the photonic crystal fiber, and we call that as a photonic crystal fiber when these holes are in the hexagonal shape. So if you take any layer, every layer will have a hexagonal shape, but this one is not exactly hexagonal. We call this as the periodicity is a bit broken. We call that as a photonic quasi crystal fiber. Instead of having the hexagonal shape, it can be changed to other shapes also. When you change the structure, then the property it become different. So for different sensing thing, we need to make it as a different structure. So there are a lot of researchers around the world, they try to do different kind of structuring and making the cavity and the height of the cavity and the kind of the gold plate or the silver plate and what medium we can use that. All this kind of research is going on. So we need to do thing about the source. We need to do thing about the medium, that is our fiber or the microstructure or the metal coating and everything, and also finally the detector. All these three things, and practically we need to see that whether we can fabricate that easily, okay, or at least if it is difficult, but at least it is feasible. That is a big question. So some of the microstructure, theoretically we can say that, okay, come on, if you do this kind of structure, it can work, but can it practically possible to realize it? That is a big question mark. So we need to answer that also. So recently, with the collaboration from VIT with Sendil Sivabalan and Ramesh Babu, my PhD student Soda Chu, who just graduated very recently, a month ago. Now he joined as a postdoc at University of Strathclyde in Glasgow. He has done a fantastic work of 4 papers based on this structuring, and then what are all the properties. Even though we say that this is the structure and the whole size and the thickness of the metal plate and everything, but in reality, when you do that, we won't achieve the exact thing. So there is a tolerance of, let's say I want to say I need a 100 micron of thickness, but the 100 micron can become a little bit more or a little bit less. So the tolerance study has to be done, because practical thing, we need to understand how those kind of changes is going to affect my sensor and those kind of thing. And all those studies he has done for 2 or 3 different kind of structures. And practically he has done a lot of structures, but useful things we came about with 2 or 3 structures and some good properties about that when we make fabricate sensors based on that. And all those 4 papers, now you got the 5th paper also published in the IEEE journals. So that's the overall thing I like to talk about this photonic crystal fiber and the light source, the medium property, and then finally the detector, how all these things, naturally they are all happening and occurring, and all things are detectors, okay? Even our skin, if it feels the heat, okay, I'm sitting next to the sun, it feels the heat, is a sensor, it is feeling something that I feel that the sun is very hot, the day is very hot, the temperature is very hot. like that. So everything is a sensor. Naturally, they are all available, but the humans nowadays are getting more closer to define that in a very shorter scale, or whatever the scale I want in time domain or frequency domain or in the intensity domain, and everything we are doing. And still a lot of research can happen, because research cannot stop. And we may come to know about a lot of more things, and we may have even better sensors or even better communication system or something like that. So thank you very much for everybody listening to my talk.
Thank you, Dr. Nakiran. A very wonderful talk. And there are some doubts. I request the participant, if you have any specific doubts, you can post it in the chat.
So there is one question in chat box, sir.
Yes, sir. Comments on permittivity and permeability. Somebody discussed about permittivity and permeability. These words are frequently used by you. So they want to know about the permittivity and permeability.
Yeah, okay. I mean, if you remember, we learned during our school itself the capacitor and the inductor, which is the capacitor is based on the electrical charging property, and the inductor is on the magnetism. So any material will have its own electrical permittivity property and then magnetic property, which is the permeability. The word itself is the permittivity comes from how the electrons can permit the flow of the current, that decides the permittivity property. And the permeability is the penetration of the magnetic field into the medium, or how magnetic it is decided by the permeability. So these things are derived from the susceptibility property of a material. So if you want to know about how the material or the medium is going to behave for our electromagnetic wave, we need to know about both the permittivity, which is epsilon, and the permeability, which is mu. And one of the biggest invention of Einstein is he just said that the permittivity of the air is epsilon naught. It has a fixed value. The permeability of the air is also a fixed value. We call that as a epsilon naught or mu naught. And actually, if you take the square root of that, square root of epsilon naught multiplied by the mu naught, reciprocal of that will give us the speed of the light, which is 3 into 10 to the power of 8 meter per second in air. If you take the permittivity of the air and the permeability of the air, multiply those two values, take the square root, and take the reciprocal of that value, it will be exactly 2.998799 into 10 to the power of 8 meter per second. So these properties are very, very, very important for any medium or material interacting with electromagnetic wave. Electromagnetic wave has both electrical wave and then the magnetic part also. So the medium, because of the electric part and the magnetic part, the epsilon and the mu, the permittivity and the permeability will interact with that based on that.
Thank you, Professor. Actually, another one question is from Girish Chandrasekhar. Is this work focused on the transmission of the signal or its detection?
Okay, that signal transmission, in communication, we say it is a transmission because we want to send the ones and zeros to the other end. We don't want the medium to interfere with us, okay? But we have to send through the medium. There is no other way, because I'm sitting here, you guys are sitting in somewhere in Vellore or somewhere. I want whatever I say or whatever I want to show it to you, exactly reach it at the other end. So the medium interfering with the signal or whatever the thing I'm saying, I don't like it. So the transmission has to be very perfect. So in communication systems, we want to see that the medium is not influencing my signal and no distortion given to that, so that I can have a very good transmission and everything will happen. But in the sensor system, it's the other way around. I send a signal and I just wait for the medium to interact with that to tell what the medium has with it. And then whatever the interaction, the signal will feel that, and the detector will detect that and tell that the medium is this. Exactly the example I said when the air is not, even the visibility. If you go to the weather report, every day they will say tomorrow there will be this much temperature, and then the sunrise time, sunfall time. Also, they will say that the visibility, how far we can see, okay, from the window, how far we can see. After some distance, it will become very foggy or mist or because of dust or something like that. That means we can say that the transmission of the light getting affected because of that. This is the part of the sensor part. That's the sensing part, and the detector has to sense that. So our eye is going to sense that there is some dust or mist or fog in the air.
Actually, he asked the same person has asked another question. It's, does the distance or length of crystal fiber have any effect on the signal transmission?
Yeah, of course. I mean, they have, because if it is, as I said, let's say the source of the light is too far, then the light received by us will be less, right? The loss in the medium, the length of the medium will decide how much loss it is going to be. If it is a pulse, then how much dispersion it is going to be. So we have to take that into account as well. If it is a sensor, then while calibrating, then we have to take into account what is the perfect length or the so close perfect length of the sensor, which will be useful. Because for some reason, we may need a longer length sensor, because sometimes we want to know that for particular length, like between my elbow to the wrist, what is happening, then there has to be a catheter which is going through that, and the whole length has to be a fiber. So we cannot stop that length. We cannot cut it up to midpoint or something like that. So all this is coming under the design of the sensor of the fiber, definitely. Yeah.
Thank you. Thank you. Another one question is very basic. How stimulated emission happens in laser light? I think it's a very general question, not related directly to the presentation. They asked about how the stimulated emission happens in laser.
I mean, I can
due to the passing of electron.
Give an example, like let's say, I mean, this is just a property, right? Like, let's say I wake up in the morning in my house, something is very bizarre things are going on. My wife is scolding me with a lot of things. I go with that mood, excited mood to the office, and some student come and ask me doubt. Then I yell at the student because I'm in the excited state, and something coming and interact with me. Then I give out in the same mood. So like that, when an atom having an electron excited to one level, so there is a energy level gap, the photon wavelength, and I mean the frequency multiplied by the Planck's constant will tell us what is the gap between the lower energy level and higher energy level. Let's say there is an incoming photon of the same energy level, then that will stimulate this to say that, okay, you are at the same energy level, come on, let's go out. Then that the photon which is keeping the electron to the higher energy level, that will make the electron to go down, and that photon also come out. So the influencing photon, which is stimulating this atom to go down from the excited state to the ground level state, and then the coming out photon will be exactly in the same wavelength. They are called the coherent photons. So they become a pair. So those two can go and stimulate other two atoms. Then it becomes 4 become 8 becomes 16. Then the source can be put up in a resonating medium that become a laser. So that is a stimulated emission laser radiation.
So I think another is, you was saying something about detecting the blood or urine sample using this sensor. Could you elaborate on this?
Yeah, I mean, you can either use it as a in visio or external one. I mean, you know, the endoscopy and the laparoscopy, they send a catheter or something like that. Let's say they want to measure some glucose content on a particular part of a body. Then what they can do, they can design this sensor under the fiber tip with this cavity and this gold coating and everything. When you send it through the catheter, then when the blood touches this place, the refract index of the blood will influence with the refract index of the gold plate, and the light which is, we send it from the external through the fiber, will go and feel that change in the refract index, and the light reflected coming back, we will know that what is the refract index at that point of the glucose which is touching the fiber tip. Okay, then that refract index will tell us how much is the glucose content in the, because we have a standard chart that different glucose concentration level, the refract index of the blood level is different. So we can detect through that.
Yes, yes. Actually, is another student have asked whether biosensor are prepared using polymers.
Depending on the material, because we want to know that whether it is internal or external. If it is an external, like we take the blood out and then we put it in the fiber external, then the rules and regulation are not very stringent, because it is outside the body. We have different rules and regulation. But if you are sending anything into the body, then we need to take care of all the material property and whether it is an allowed property and all those things. So there are standards in the medical science. There are institutions which is keeping the standards. So we need to prepare the material in that way. So they may not allow the glass to be sent through the body. Maybe the polymer material is okay, and things like that. For example, even the spectacles I am wearing, it is not made of glass anymore. It is all polymer nowadays. So they are all polymer glasses. So the polymer technologies are developed so much, and they are very good, and it is very safe also. So we try to do it in a way we want.
Thank you, Professor. It's a very excellent presentation, and I think most of the questions are over. Any other questions from the participant? Okay, Professor. Just I have one small doubt about the practical. Is actually most of the work I have reported is the theoretical results. So, what are the challenges if you may get while fabricating the actual sensor using this?
One of the
this type of
main
fibers.
idea of my students Soda Chow's work was the metal coating. Previously, the coating were all on the holes, the inner holes. So the crystal fiber has holes, and they need to do the coating, internal coating, inner wall of the holes. That is a very difficult thing. Even it is possible, but the technology very costly and very difficult. So what Soda did, he just made instead of putting the gold plating in the holes, he polished the fiber and made a cavity, and it is a open one. Okay, don't take the blue one as a closed one. It's actually a open one. This is just to say that there is a circle here. Okay, so now if you put the metal coating, is very easy. It is a open length. It is like a hair, and you make a cavity in that micro cavity, and you just coat it with. It is like putting a glue on the cavity. So this is very easy. Now the technology is there to do that. So it's much easier than putting the inside wall of the holes.
Okay.
So most of the practical challenges, like the theory people may try to give an idea, and then when they try to get it done experimentally, there may be some problems or the challenges come up with. Then when they publish those results, the theoretical people may try to get some solution for that, and then a new technology can come for fabrication and practical implementation, and it goes on. It goes hand in hand with the challenges coming with the practical cases and what should be done to solve the problem through the theory, and then the practical fabrication again. It keep going.
Okay, that's very informative presentation, and I think everyone enjoyed your presentation. So the feedback also came. They are really they enjoyed the presentation. So I thank Professor for your time, and on behalf of all the conference convener, I thank once again. I thank all the participants for your time. Thank you, Andala. Thank you.
Thank you very much.
Thank you, Professor. Thank you. Thank you, Nax.
Thank you, Professor Nakiran. Thank you for the nice talk.
Okay, on behalf of conference committee, I really thank Professor Nakiran for his wonderful talk on light as God, because even though we are in a pandemic situation, we all are get connected because of the light. Thank you, Professor.
Thank you very much.
Yeah, thank you, James.
I also thank Professor Sivabalan for spending with us and sparing valuable time to chair this session. Thank you, sir.
Thank you, sir. Sivabalan, sir. Thank you.
Thank you, sir. Thank you.
Sivabalan and Nakiran. Thank you.
Thank you, sir. Thank
See you next summer.
you. Sure, Nakin. Thank you.
Okay.
Sure.
Thank you. Bye.
Thank you.
Always welcome.
Yeah. Thank you.
Thank you.
Professor Chandrasekhar. Professor Chandrasekhar.
Time it, sir.
Time it.
Welcome, Rajan Prabhu. I'm Rajan Babu.
Hello, hello. Can you hear me? Hello.
Yeah, yes, sir. Yes, sir. We are hearing you.
Okay, thank you.
So, Chandrasekhar, sir.
Yes.
Yes, sir.
Okay.
Welcome, sir. Welcome.
Welcome. Very good evening.
Good evening,
There
sir.
was
Good evening, sir.
Good evening. There was some
Yeah.
technical glitch in my
Oh,
side.
okay. No problem, sir.
Okay.
Sir, Dr. Rajan Prabhu is our speaker today.
Okay.
Now, Dr. Madheshwaran will continue the session, sir. Please.
Okay. Thank you, sir.
Sir, welcome, Chandrasekhar, sir.
Thank you.
So now we are going to, audience, we are going to move to the last talk of the session. And now I request Professor Chandrasekhar, Director, Center for Nanobiotechnology, to chair this session.
Thank
Over
you,
to you, sir.
Dr. Madheshwaran, and also thanks to Dr. Professor Rajan Babu, sir, to give this as an opportunity to chair this session. So I welcome Dr. J. Rajan Prabhu. He is from Max Planck Institute from Germany. And he has finished his bachelor's in physics and master's in physics from American College, Madurai. So thank you very much. I also did my bachelor's and master's from American College, Madurai.
Yeah, what a coincidence, sir.
Probably Professor Rajan Babu made it. Probably he knew that I am from American College, maybe. So I did so. And Dr. Rajan Prabhu has done his PhD from Indian Institute of Science. And he has done on structural studies on mycobacterial REC-A and RUA proteins. And also he has done a postdoctoral research from Indian Institute of Science on the same concept what he did during his PhD. Also, he did another postdoctoral program in Max Planck Research Institute of Biochemistry. I also did a postdoc next to his institute. That was a forensic institute next to Max Planck, not in Max Planck. I was also in Germany. Maybe a lot of coincidences are happening here. So he was in Institute of Biochemistry, Department of Structural and Cell Biology from Germany. And now he is a group leader and senior scientist from Max Planck Institute of Biochemistry and Biochemistry, Germany. And he has a lot of technical experience handling molecular biology, cell culture, and protein biochemistry, and protein biophysics, RNA biochemistry, electron microscopy, single particles, cryo-electron microscopy, X-ray crystallography, so on and so forth. And he has also published a very good paper in Nature and Molecular Cell. And also he has a paper in PNAS, and he got a very good fellowship program from EMBO, which is a very prestigious program, which has paved his way to his postdoctoral research in Germany. And also he obtained CSIR research fellowship towards his graduation. Now I welcome Dr. Rajan Prabhu to take this session and give a talk. His talk, I forgot his talk, just hold on. So he will be talking about and just hold on, sir. I have some problem in my system.
No problem. I can continue. No worries.
So I welcome Dr. Rajan Prabhu to give his lecture on the topic, the revolution in structural biology. Welcome, Dr. Rajan Prabhu. Now you can take the session and give your talk. Thank you.
Thank you so much. That was probably one of the nicest introduction I ever had. Even I myself was looking back at all those times of American College. And anyway, thank you so much, Professor Chandrasekhar. That was a very warm invitation, very warm welcome. And before we start, I would also like to thank VIT for the invitation, especially during Corona when everybody is at home. It's a good time to learn, to be honest, because if you're at home, we have lots of time, hopefully. And then also, I would like to especially thank Professor Rajan Babu, who reached out to me, as well as he was very kind and helpful to all my questions and stuff. So I'm going to share my screen. Please let me know if it is shared. All right. Can everyone confirm, please, that you can see my screen?
Yes, sir. Yes, sir.
Okay, wonderful. Thank you. So as introduced, my name is Rajan Prabhu, and I work at Max Planck Institute of Biochemistry. It's actually in south of Germany. It's close to Alps. It's only 30 minutes drive from the institute, to be precise. It's a very nice city. We actually also live in something called Campus Martinsried, in which we have LMU, which is Ludwig Maximilian University, as well as we also have Biocentrum. We have 2 or 3 international PhD students program. In case if anyone is interested, please go through them. They're really, really helpful and good schools. All right, so originally I planned to talk about some of the biological questions that we're trying to address. But when I got the list of all the speakers, I found my talk was pretty, pretty outside. Of course, it's a transdisciplinary conference. So I kind of expected that the people are actually from different backgrounds, not especially from biology or not especially from physics. So I tailored my talk in such a way that it can actually reach all the background people. Also, then I will also touch upon some of the really, really basic elements of biology for a physicist and physics for biology, so that everybody stay connected. So what can be actually more interdisciplinary or transdisciplinary than biology? I myself is a physicist and then did my PhD in biophysics, moved to biology. To be honest, biology actually needs interdisciplinary people. It's such a wide field. It has space for everyone, being a mechanical engineer, data scientist, machine learning, whatever you want to do, there is a space in biology. Actually, there are so many questions which can be addressed if you actually start in biology. In a way, it's a true interdisciplinary these days. Right, so, I'm just gonna today give you a flavor. It's not a detailed one because I'm actually covering quite a few heavy concepts. So I simplified enough. I hope it's really reaches, but it is actually what happened in the last few years is nothing sort of a revolution, which kind of speed the way we do structural biology. I mean, I will cover up first macromolecular crystallography, which is actually what we basically was doing so far, and how the revolution happened with electron microscopy. I hope I have time. It's a very brief touch up on electron tomography. A disclaimer, I know I do and publish on both the techniques. I'm actually learning this technique. So it's only gonna be information, not from any of my papers. Right. Okay, so it's really, really exciting time to be doing biology, especially structural biology. What I really hope to achieve by the end of the talk is that I transfer some of the excitement that I have to some of you who are in the audience. As I said, I'm going to slightly spend 5 minutes in the biology for the physicist, or I mean, we all studied in school, I'm very sure. So we all know what's a gene. We all heard it. So normally genes are transcribed to mRNAs and mRNAs are transcribed to proteins. This proteins is nothing but a sequence of amino acids, which is not, it's a very simple, it's only 20 amino acids possible. And these amino acids actually form a linear chain, as you can see from here. It just forms a linear chain. It's only these 20 amino acids in all possible ways. And this is actually called the protein sequence. And oops. And then, and then these protein sequences, which is a linear single chain, can form 2 kinds of secondary structure. They can form alpha helix. They can also form beta sheets. And these can form and fold into something called a domain, a small domain. And these domains can form with the multi-domain protein, or one protein can have many domains. It's actually called the quaternary structure of protein. So we started with a gene, we went to protein, and then we have secondary structure, we actually form a structure. And these proteins can be as small as like 40 amino acids, means the 40 amino acids that I showed you before, or it can be as huge as, it can be as small as say 10 kilodalton, as huge as megadalton protein like this is. In this case, this is actually a ribosome. So they come in many flavors, they actually exist in different forms, because these small TRP cage can actually form multi-layers and actually can form even bigger than this. That's also possible. They can exist monomer, they can exist dimer, they exist small, they exist big. It's variety of reasons, variety of structures possible. I mean, as I established what a protein is, I don't have to explain people that we all heard of hemoglobin, and we all heard of actin and myosin, and we all certainly heard of keratin, which is in the skin. Actually, the proteins are actually the workhorse of the cell. You go anywhere in your body, you have a protein working for you. Even digestive enzyme, you eat food, there are some enzymes which comes and digest food. So protein is essentially the workhorse. It is so important. And why do we really need to study? I'm just gonna quote what Francis Crick said in 1988. Everything happens in a molecular level. If you really want to understand something in deep, you need to go to molecular level. And why so? I'm gonna give you an example. We all are in COVID situation. This is nothing but COVID proteins bound to RNA-dependent RNA polymerase. This is one form. The RNA-dependent RNA polymerase has to bind to RNA. Okay, how does the protein look without the RNA? How does the protein look with RNA? I'm sure most of you would have heard this name, remdesivir, which is nothing but the viral inhibitor, which is also used for treating corona. You would have heard it. So how does that drug binds to that protein? So what I'm trying to establish here is that it is so important, it is so vital for humankind and for everything to study the protein structures. Oops. All right. So there are different questions you can ask in the structures. Some structures reveal the structure and function, which means how can it do? Does it move? How can it bind to the next protein? What is the molecular image of biology that you're using? Or you can even go further down on a finer resolution. You can actually mutation. What we mean by mutation is that, as I explained you before, proteins are nothing but a linear sequence of amino acid. One amino acid can be mutated into something else, and that causes a disease. If that causes disease, how does it work in molecular level? This is what we are looking at. And then, of course, as I said in the case of remdesivir, we actually can look how the drug binds to the protein and then probably design better drugs. Having said that, we actually mostly have three methods of structural determination. First is the nuclear magnetic resonance, which I'm not an expert at, I don't use it, but it's actually a very, very good technique. The advantage is that you can actually just drop your protein solution into the machine and then measure it. Of course, it's not as easy as I say, but it actually works very well. The only limitation is that the larger the size of the protein you go, it's difficult to solve the structure. The most workhorse for most of us, actually last almost for 2 decades, is actually crystallography. What you do is that you take your protein, you form crystals out of it and put them under the X-rays and solve the structure. Solve the structure means you determine the protein structure. It actually can give you really high resolution. It can give you really, really highly atomic details. The only problem here is that you need to have that crystal. I mean, I'm going to touch upon that later. Actually, almost half of the talk is only that. You really need crystal, and the crystal have to reflect. And then there's something called phase problem, which I'll cover later as well. Oops, okay. And then I have something, we have the new one, which is electron microscopy. If you ask 5 years ago, we actually, to be honest, I should also apologize, we called it as a blobology because it only gave protein structures of very, very low resolutions, meaning you can actually look at them as a domains, you can look at the protein domains, but you really can't look at the atoms into it. But this has really changed, and this is actually going to be the essence of the whole talk. But to establish that, first I will explain you what is crystallography and why we are moving from crystallography to electron microscopy. So as we said, if you really want to study a question in mind, you actually need to have a sample, and you need to have a question in mind, and you need to have a target protein. So we actually start with the gene sequence, then we actually clone them. What does mean is that when you have a gene sequence, you just cannot get a protein out of it. You need to put, imagine if I take a gene sequence from a human, I have to put them in a bacteria or in a yeast, ask it to express that protein, because it's not easy to just have your it's not easy to just extract protein from a human. It's not that I'm gonna take you and take a blood out of it, purify it and crystallize it. Even if I do that, it won't be enough. So what we do is that we actually use host organism, and then we clone into them, induce them, and then we purify them, we form crystals out of them, we collect data, and then we determine the structure. I'm gonna go spend a few minutes on each of them. I may slightly rush through. In case if it is rushed through, just let me know, I will actually stop it. As I explained, the idea is that you need to know what you're going to study. You need to study one protein, you need to study a multi-protein complex, or you're going to study a big complex that you're going to purify out of your blood. Once you have that, you need to know you're going to endogenously purify them or you're going to overexpress them. The moment you do, you actually can do it. But before that, we actually need to do something called construct design. What is that really? Okay, this I already, and construct design means, what is construct is that, imagine this has 1000 amino acids. So this N-terminate starts 1 here, ends at 1000. Okay, so construct by mean is that it can have two domains or 3 domains. We need to design where we want to cut and express the protein. What does that mean? If you look at here, if you look at here, this protein has a really, really long protein, and then this has 2 domains connected by an unstructured region. If you want to put an unstructured region, try to crystallize, good luck with that, because the flexibility is actually against crystallization. The moment you have flexibility, the crystals won't get ordered. I will also explain in a minute why. So what do you do with the rational design construct? You only take kinase domain and actually crystallize them. Or you only take the polar box domain 1 and 2 and then crystallize them. This is much easier. If it is complicated for you, I have a slide to make you understand how does that, what I really mean is that you really need to make the protein devoid of any flexibility, devoid of any of moving parts. In a way, it's actually equal to, you need to actually having a haircut. You really need to have a good haircut. All of us want to have a good haircut, but you really have to be careful not to cut so much. Then you may end up like this. Then what you do is that you actually remove a structurally or a functionally important protein, important region, then you end up with the inactive amino acid. You don't want to do that. Well, some people may still like the hairstyle, but that's not how it works in biology. Right, and then you also need to have a really, really pure protein. The demand on protein purification is so high, it has to be at least 99% pure. And that does take so much time, so much of your time. So whatever the fancy protein structures you see is actually 99% of people working on the bench trying to get your structure or trying to get your protein as clean as possible. I slightly go through this. The nickel affinity is that what you do, you add something positively charged chemical to your protein, and then you actually pass through a negative chain. It actually binds. All the rest of the things which is not bound is actually going to wash away. And then size exclusion is nothing but you kind of separate them based on the size. So the demands on protein purity is really high. Also the stability. So this is the 3-protein complex on day 0. You don't crystallize on day 0. You wait because the evening you want to go out with the family, friends, whatever, and then day 1 it goes down. So this actually also demands lots of time and energy from you. Of course, you can also be lucky because crystallization itself is a purification process. So it could be lucky that you put a dirty protein in and you get a crystal out of it. It's possible, but it doesn't happen all the time. Or you can actually add all the cofactors, or you can stabilize them, you can add inhibitors. If you have a flexible protein, add another protein so that the flexibility is arrested. There are so many ways. But I should say the crystallization in macromolecular crystallography is one of the least understood topic. We just cannot predict it. So what we do is that we go empirically. Right, the next question is the crystals. What are crystals? They're nothing but closely packed arrangement, same arrangement in 3 dimensions. It's the same in X dimension, Y dimension, Z dimension. It's just nothing but a clear repetition of the same thing again and again. Actually, crystals can grow very large. Actually, if you look at the crystals in Mexico, these are people walking along the crystals. You can see how big those grow. But in our field, we're not lucky enough. Our crystals are maximum of only 100 microns. It's not bigger than that. Bigger is better, but it has to diffract as well. Right, so what we did so far was that we had a protein of interest, we cloned them, overexpressed them, purified them, and then crystallized them. And then we need to collect data. What do we collect data? The experiment is super simple. You pass X-ray to the crystal, and then you collect the data or diffraction spots, and then you actually derive an electron density. This part I will touch upon later. So you also have to rotate the crystal. Actually, each slide can be a 1-hour talk, but I'm actually simplifying it for the wider audience. Okay, so comes the real problem. Actually, I'm actually gonna put a little emphasis because I was also stuck here. So this is actually 100 micron or even smaller than that. You actually mount them in a loop and then you freeze them. Why you freeze them is because you don't want to have radiation damage. You collect them and then you really get data out of it, and then you devise the data and then you collect the data. Also, the collection of the data depends on 2 things, what you really want to do. And then if it doesn't do, you go back to bench, make your construct better, and then you do a much better job on the bench, purifier protein, less flexible, then you come back, make a new crystal. It's actually a cycle. We go along the cycle all the time. Once you have a data, you need to determine the structure. So the easiest way to do would be the molecular replacement. The idea here is that imagine 2 protein sequences actually have a similar protein sequence identity or a similarity. So I have a, say, polymer of, say, 10 amino acids, and someone else, say, Prof. Chandrasekhar, has a polymer of 8 amino acids, out of which 6 are similar. Then we actually expect that they form a similar structure. So what we do, we take the data, we just replace the molecule with the other one. And then there are 2 more sophisticated methods. This was used before. This also got what Nobel Prize for Max Perutz, is that what they used, that they actually used the heavy atom inside that, and then because they first solved the heavy atom structure using direct-based methods, and then extrapolate that to the other ones. Nowadays, we actually don't do this because we do in a different way. We actually do something called fancy multiple wavelength anomalous dispersion, which is pretty good and solid. But the most of the bottleneck actually comes from having crystals, because it's absolutely not easy to have a crystal. I'll give you my real life example. I came here to Germany in 2010, 2009 as a postdoc. In 1 year, I purified it, I crystallized it in 1 year. So I really was very happy. Oh my God, I'm really going to be the most successful person in the world because it was such a hot complex. And then for next 6 years, it did not diffract. Though it formed the crystals, it did not diffract for 6 years. That was so frustrating. Though my other projects have worked, but this is really so frustrating for structural biologists because first of all, it has to form crystal. That itself is a big thing. Even if it forms a crystal, it has to diffract. Mine was diffracted with 7 angstrom for 6 years, for example. And then it repairs large amounts of material, meaning at least we need 10 milligram per milliliter of proteins. That's actually nothing small if you really compare to, that's a lot of effort, especially if you're working on a multi-protein complex. That's a huge amount of effort you need to record that much of a material. And also flexibility. If you have a structure, if you have a protein which is very flexible, it's absolutely not easy to crystallize them. In addition, phase problem. But in my opinion, phase problem can be easily overcome. The main problem, bottleneck, is actually crystals. You can have a very nice project. You can design a very nice project. You can actually have a very good question, but first bottleneck is the crystallization, and none of us really understood why it forms crystals. If any one of you can understand how a crystal forms, then probably you'll get a Nobel Prize because it's actually not easy. And this is where the problem was. So wherever we got crystals, we proceeded with the project. If not, we changed our question and moved on to a different project. This is where the new hero, electron microscopy, comes up. As I said, only 5 years ago, it was not possible, and only now it became possible. Why? Okay, first I go to the question why. Mainly because they actually have something called direct electron detectors. All of you know, before we had something called CCD, charge coupled device, which means electron is converted into current, and then that current actually is measured. Here you actually directly measure, actually directly count how many electrons are hit in your pixel, because you have larger pixel. It's also speed and sensitivity, means you actually can measure really 300 frames in a second. That gives a huge boost, because whenever the electron hits your sample, the sample actually moves. Means when you have such a speed, you can actually align for those samples. You can align and actually get enough signal out of it. And then, of course, there is lots and lots of new powerful image processing algorithms came using maximum likelihood that completely sweep the field. What are the advantages? We don't need a crystal. That itself is an advantage. We really don't need a crystal. You don't have to be stuck for 7 years. To give an update, my project, I actually moved on to start a group, but then the lab did microscopy and then solved the project in 6 months, which I was struggling for 7 years. You know, how frustrating. I mean, in a way, it's good also. So it only requires really, really small amount of material. So I told you we need probably 10 mix per mil. Here we only need 0.3 milligram per mil. That's a huge advantage for a biochemist too. And then since we are not, okay, in the crystal, what you do is that you put one on the next in the crystal, so they are actually arrested. Here it's not arrested, which I will also come to it later. So it's actually can have different conformations. And if it is discrete, you can actually capture them. So we all were like struggling with X-ray crystallography, and then this structure came in 2050. It's actually from Subramanian's lab. And then it was 2.2 angstroms. We all were heartbroken because our bread and butter was crystallography. And then we all actually also thought probably it was easy. No, it's actually not. You will actually see why. So this was probably for me kind of an, how do you say, a time for me to decide that I have to switch to electron microscopy. Right. As with any sample, you still need to go through the same process. Only thing here is that you don't have to design the construct as it was before. You just put all of them together and you still need a good sample. A high purity sample is a must. Right. So what we're going to do is that it's going to be, I'm going to show you some movies so that it will be much easier. We have something called EM grid. We held it by forceps. We actually apply the protein sample here and then we blot them out. Why we blot them out? Because we really want to have a single layer of particles. You don't want to have a multiple layer because you're going to pass X-rays to them and then get the projections. If you have one on the other, you will not have a clean projection here. So that will actually disturb your algorithm. So what you really want to have is that really nice thin layer of particle which does not overlap with each other. And this is how the electron tomograph look. So how do we do? I'm just going to show you a video. I hope it plays. Yeah, so this is how the grids are. As I'm showing you the video so that you can understand the scale of these experiments. You can see these are really, really carbon coated grids. They are like 1 micron. The size is actually about 3 millimeter, but the holes are inside actually are about 1 micron or 2 micron, depending on what you want to do. These are really, really small ones. They are actually covered with carbon. I'm going to show you how we do. So what we do, we apply the protein sample. It's not playing, does it? Go ahead. Move. Oh no, that's okay. So what we do is that we apply the protein sample and then we actually blot out the excess, because you really want to, what you really want to achieve is that you want to have a single layer of protein molecules. You don't want to have overlapping layers. This is how we do. Actually, this is a little old video because we were doing it manually, but nowadays you have sophisticated machine which can actually do it for you. If you're really young, you don't have to do much because the machine does it for you these days. This was a dream before. And then once you completely blot them out, you actually plunge freeze them into liquid ethane. Why liquid ethane is also a different question. Actually, the 2019 Nobel Prize was given to Jacques Duberger for actually finding this process. Liquid ethane is very important because it actually has a really, really rapid cooling. Rapid cooling rate. It also has a no Leiden-Foss effect. Actually, it's Vellore. So you all have seen how the dosa is made. So when you put water on it, sometimes if the surface of the water is actually hotter than the boiling point, it will form a vapor. It will destroy the sample. So with liquid ethane, that doesn't happen. And then it's actually not only that you want to vitrify your sample, you really want to, sorry, not only that you want to freeze your sample, you really want to vitrify, because If it forms ice, it's going to be too thick and you won't get anything from the microscope. So what you really want to do is that you want to do vitrification, not anything else. So handling has to be very, very important. Otherwise, it's going to be so messy. And then once you make your sample ready, you're going to put through electron microscope. The electron microscope has a condenser lens system, which essentially makes the beam bigger or smaller. Then you actually put your sample here. That's where your sample resides. Then you also have an objective lens because you want to focus on the area of interest. Then you have projector lens system. Unlike the case of normal analog microscopes, in electron microscopes, you only have a given samples of quantums of magnification. You really cannot have you cannot have any number, but only the given numbers. And then sometimes we also use energy filter to remove any incoherent electrons. And then we spoke about the detector before, and then we collect the data. The scale of this experiment is huge. Nowadays, don't go away. Nowadays, look at this. This is actually 4 meters high. We call it microscope. I mean, but it's a huge help. And then what you do is that once you put into the microscope, and then you collect the data on different regions of the grid. And then this is what you get from the different regions of the micrograph. This is what you get. So yeah, we actually normally record, say, 10,000 micrographs in total, and then you can sometimes end up with 1 million or 5 million micrographs. Then first thing what you need to do is that you need to pick particles on them. How do you pick them? You see, it's a nice circular shape. Then you actually look where and all these circular shapes are there, you pick them. And actually then you look, there's another view. Okay, that looks nice. Then you actually pick those. Similarly, you actually pick many, many particles on this one micrograph. Similarly for 10,000 micrographs that you collected. We were doing it manually. Now you don't. There are so many algorithms which can do it automatically. Then what you do is that you need to pool and align particle which looks similar, which we call it classes. You see, this all the particle which look like this will be aligned into one class. All particle which has another view will be aligned into one class. Ideally, what you want to have in a micrograph is that all possible views should be filled in your micrographs. As I said, you also then what we do is that we 2D classify. This is a really nice micrograph. Sometimes what you get is that you actually get a dirty micrograph. You will also get an ice cube here, ice cube there, something else, contaminations. So by doing a 2D alignment, you also kind of get rid of those contaminants. Right. So next thing, how do we do the particle alignment? It's actually super easy. I mean, to some extent, it's actually 3-parameter problem. You need a shift and the rotation, right? So you actually need to shift in the X and lift in Y, and actually also have to rotate so that you align the particle on each side. So what you do is that you rotate, you actually look at the correlation coefficient with the shift. Where the correlation coefficient peaks, you actually take that as a particle. But how do we? So now what you have is that set of 2-dimensional projections. How do we go from 2D to 3D? That's a big question. Let's imagine that you have, this is your sample, like you have 3 dots. And then you just look at, if you have only one projection, means you look at this line. If you look through this line, you will see this. Imagine you also look at 3 different ways, 1 way, 2 way, 3 way, or 3 projections rather. Then you actually can start to see that where this actually 3 points are approximately. When you have 5 projections, it becomes even more clear. When you have 13 projections, it's absolutely clear where they are. But if you have 25, there's absolutely no question at all. You can clearly say. So this is something called back projection algorithm. This is what we actually gonna do with our stuff. And also there's something called Fourier slice theorem, which is a little mathematical. So this is what the projection you have. And then what you do is that you take a Fourier transform of the 2D image. This is actually nothing but the central section of the 3D. So you arrange them in 3D using Fourier space. You take a reverse Fourier transform, you actually get the 3D. So I'm just going to explain this, explain the back projection a little clear here. It's a movie. As you can see, these actually particles are projected on this direction. As you can see, we also have many, many different particles in the same micrograph, and they may actually belong to a different orientation. So what you do, you pick those particles, align them, and then you assign those particles the Euler angle in case, where do they belong, and also the rotation as well as the translation. And then the moment you arrange few particles, then what you do is that the moment you have more and more projections, you can actually pick more particles, and then you actually have the back project them, you get a complete model. It's a very simple concept, but it really works well. As you can see, the more and more projection you have, or more and more particles you have, you actually get the structure really nicely. It's actually a whole structure. Now we can get even much better resolution than what you have. I hope that was clear. Oops, no, okay. Right. So this is exactly what we do. We take projection images, we align them, take them Fourier transform, and then align them in the Fourier space, reverse Fourier transform. You actually get it's a central section theorem. It's a very well-known theorem. What happens is that, of course, your aim is to have particle at different orientation. It's absolutely possible that you don't get all the views. You can actually have holes in the views. It's absolutely possible. That's where it comes to become a problem, because first of all, you need to figure out the orientation. And then sometimes the biological samples are really made up of carbon, nitrogen, oxygen. It's not a very heavy materials. So you actually sometimes have a very low signal to noise ratio. Sometimes you also can have a different ensembles of protein exist. One can exist this way, one can exist the other way. These are all can be a real issue when you want to reconstruct them. Also, though you purify them 99% clearly, it's very much possible that some other protein comes into your sample. It's also, you have to be very careful. There was a famous incident in 2014 with the HIV trimer that somebody reconstructed, which is ancient from mice, very well known. So you really have to be careful. But these days, the algorithms are so powerful, you don't have to worry much about it. Right. So I'm just going to summarize this. So we did a 2D classification, and then we actually made a 3D initial model. And then the 3D model can actually have different classes. Like 2D can have different classes, like 2D can have different views. The 3D can have different orientations. What I mean is that you have two protein complex, they can exist like that, they can also exist like that. So this is actually called 3D classes. It usually requires the initial model, and then you have to group them based on the angular assignments as well as the stoichiometry and conformational change. In this case, you can clearly see it's a kind of a cylinder. If you look from the top, that's a projection. You see, if you look from the side, you see it here. And then the moment you do, you completely classify out the junk, you get really nice, you get such a nice proteasome. Just to summarize, so we actually get 3D reconstruction from set of 2D projections. Usually we start with particle picking. We go to align them, classify them, also remove the junk. And then we actually iterative alignments. We go back and keep doing it, improve it. You want those set of particles which has that one set of conformation. You can have different conformations, but you need to carefully process them to separate them into many views. And of course, it is computationally very expensive. You require a cluster. With the invent of new GPUs with CUDA programming, it's much faster, but you still need a very good solid backup of having a computer. And how much time I have? 1 o'clock. Okay, I will finish it. Okay, actually, this is what I originally planned to talk, maybe either about 88 or molecular cell. But actually, since it's a interdisciplinary, I thought instead of going very narrow into one topic, I thought I would cover. But in case if you're interested, if you came to my talk to interest in any of these, I'm happy to get connected with you later and give you the connections. So this was actually, it's all done by electron microscopy. This was actually a 20-year lingering question, how does the ubiquitination happens? Microscopy, also with very innovative biochemistry, this was possible. So another is the glucose starvation complex, which I really like to work on. Also, we continue to working on it. So another. Also, if you're interested in the case of unobvious motoring complex, the last two papers can give you some interest. Okay, since I have time, I'm actually gonna go to cryo-electron tomography, which is the most exciting stuff. I'll explain in a minute why. So far what happened was that we actually taken a gene sequence, put them into some host. For example, take a gene of human, and then you put them into either maybe bacteria or to yeast or to HeLa cells, all these stuff. You kind of, I mean, if it HeLa cell, it's okay, but you kind of, overexpress them. It's not a native environment because you really want more material for these studies. But what happened recently is that you actually grow. You remember, I hope you remember the grid that I showed you before. You grow cells on those grids. and then you plunge them, and then you take it to the microscope. So it's a native state. You don't do anything. You grow the cells and then take it to the microscope. There is no overexpression. There is no problem of treatment, nothing. You just take the cell and take it to the microscope. And then what you do is that, I mean, you can actually, you really cannot image a complete cell because it's too thick. So you really have to have something called a 200 to 300 nanometer thickness. What you do is that you do focused ion milling, which I have a movie I will show, and then look at them in the microscope. This is how it looks. And then you mill them away. This is called lamella, which is really, really thin. So it needs lots of skill to get a good lamella. You will understand why in a way. Oh, both are here. Sorry. And then if you really look here, this is how it is done. You grow the cells, you look at them in the microscope. First of all, you look at them in temp or in the side base, you look, these are the two nice chlamydomonas cells. Isn't it so amazing? You can see the complete cell, it's a side view. Then you actually take it, and then you actually put a mark because you really have to go slow. You don't want to burn the cells away. And then you pass the gallium ions. You completely burn away what's in the top and what's in the bottom. Then you have to go slower and slower and slower until you reach the point of interest. Also, until you reach the correct thickness that you need. Because if it is too thick, the microscope will not do enough transmission. It's going to absorb all the data, so you will not get any of the good information out. And then what you do is that it's only 200 to 300, and you really, really go slow. You don't have to go, as you can see, my colleague has done super slowly. She's gone to first, she moved very roughly, and then she's going slowly one by one, top to bottom. And please, I mean, I'm also learning this technique, but it's actually one of the very, very difficult thing to do. To get this real, I mean, I wouldn't say it's impossible, but get the skill of really nicely aligned or nicely formed lamella, it's absolutely, it's not an easy thing to do, absolutely. As you can see, how it started and how small it is, because orientation is wrong, something is wrong, we actually born with the lamella. And then that's how it looks finally. Right, and then you take this lamella and go to the microscope, right, on a grid. Then what you do is that you actually tilt it. That's why it's called tilt tomography. And then you take images of the same area in the different tilts. As you can see, same area is actually being imaged. But only thing we do different than single particle is that we tilt it because you really want to have a good data set. And then once you have this nice data set, what we're gonna do? We're gonna do the same thing as before. You really take a final slices. You back project. Once you back project, what you get is that you get the nice three-dimensional structure, which is a live cell. It's so amazing. I'm sorry, but it is a live cell. You see a cell which is actually no artifacts, nothing. You grow them in a image cell, and then you completely see what's inside. Isn't it absolutely beautiful? And then I actually do have one more video to show, because this is only a generic video to show how it's possible. I do have one more video which will actually give you much, much better idea of what I mean, which I hope I can play. Oh yeah. So this is the real live tomography, because you're actually gonna tilt it. This is how it will look. And the moment you tilt, so we're also gonna model it's actually from Ben Engel. You see, you can nicely see the mitochondria, you can see the nuclear complex, you can actually see all the proteosomes. You can even take the proteosomes and classify and then say, is it singly capped or doubly capped? Or you can also completely say, is it the ground or is it processing, or we can't classify them. Or you can also see something else, is it bound to membranes? If it's bound to membranes, what's the role? How does this look? You can also see all this ATPase is bound in the mitochondria. And then you can go inside and see how the nuclear complex looks. It's such a terrific technique which requires less material, which requires skill. And then, because this actually can answer many questions that we are actually lacked so far. And I hope that it's also exciting for you. And with that, I come to the conclusion. I thank Banda Schulman, who is the director of the department. The other people kindly provided some slides. I was funded by EMBO and Marie Curie. The lab is funded by ARC and Maxplan. And thank you so much for your attention. Also, please stay safe. Thank you. I'm happy to take questions.
Oh, thank you, Dr. Rajan Prabhu, for your wonderful talk on protein structure and its applications in various fields. So you have a couple of questions. One from Ramesh. Mr. Ramesh, he has asked a question. What is the meaning of you have a crystal and it does not diffract.
Correct. How to explain that? So
Then he has continuously asked one more. Is it because the ordering is not of the ordering of wavelength of light used?
No, actually, we use X-rays because that exactly coincides with the periodicity of the atom. That's not the problem. The problem is that though you have a crystal, it need not be the complete. So actually, I forgot to say, in protein crystals, we normally have 60% is actually solvent. Only 40% is occupied by the protein. Though you have two proteins bound like this, it need not be strong. It can be moving like this. It can moving like this. It can breathe. It can be formed like a smaller joint. It can breathe. Though you have a bulky, the interface could be very low. Or if you have two helices, which is longer, you will have lots of solvent channels in between. So what we actually do is that we try to introduce some proteins or arrest the gaps. This is why I said crystallography is very frustrating if it does not work. If it works, it's 1 hour, you get the structure. If it does not, then you actually really work really, I mean, you really have to be true. As in my postdoc, it was 6 years of my work, for example. So it's nothing to do with wavelength, but it's to do with the property of the crystal or property of the protein.
Okay. Next question. Just one more question. Is it possible for analyzing doping materials particle analysis using this microscope?
I have no expertise on it. I don't know, to be honest. I'm very sure the actual electron microscopy comes from metallurgy department. And I'm very sure it's very much possible.
Okay.
But I am not qualified to answer that question.
Okay. Okay. Next is very general question. Can an undergraduate work with you on some project if possible? Please let me know. Maybe one UG guy wanted to join, maybe.
Yeah, sure. I mean, okay, I also give you one more warning. Warning in the sense not because of these really, I mean, what we really show here is work of many people over many years. You know, the problem with undergrads or postgrads is that they only see the output, but it's possible. I'm not saying no, but for example, there was another paper which I wanted to show, which is Yulia Mahmoud, and she worked for 4 years to get that one miraculous data set. So when you're undergrad or a master or a BTech or MTech, you only have 6 months time, and you really need to be reasonable what you can achieve in that time. All these bosses, we actually always show only the end product, not showing what has undergone. You know, it's really huge amount of effort. Of course, write to me, so certainly we can look for it, but it depends on case to case. Depends on if you have requirement, if you have projects, because if you're coming and we have to teach you for first 2 months, then the 3 months is gone. You know, it depends on. Maybe you can, yeah, we can do, of course, possible, but not, yeah, we will see. I don't want to promise and then do later. You
know? Okay. Thank you, Dr. Rajan Prabhu, for your wonderful explanation for all the questions.
Okay. Sir, I have only one question.
Sure, go ahead.
Sir, while you are tilting the sample in that microscope, is it, how the sample is folding? Because you are tilting so many angles.
So how the sample is what? I didn't get your question.
Yeah. But whether is the possibility of falling down from the sample holder?
Okay, so what we do is that when you form this nice 3 millimeter grid, we actually clip them strongly. So we put a kind of an O-ring on top of them so that it doesn't fall. Because even a small movement, we are aware of, we don't even want to have even nanometers of movement because it's so much big. So it's actually tightly, really tightly in vacuum. It's actually clipped, it doesn't fall. Sometimes when the new students come, they don't clip well, it falls in the microscope, and we have to split open the microscope. That's a huge problem, yeah.
Okay, thank you, Dr. Prabhu. Thank you.
Okay, thank you so much.
Thank you for your lecture. Now over to chair.
Okay, bye.
Thank you very much, Dr. Rajan Prabhu. If there are no other questions, I am handing over to Dr. Madheshwaran for further action.
Thank you, sir. Thank you, sir. Dr. Rajan Prabhu, thank you very much for your wonderful talk. More resolution on revolution makes excitation. So your talk excited us actually. So thank you for your nice talk. Thank you very much on behalf of organizing committee. I also thank Professor Chandrasekhar for his valuable time and chair this session. Thank you, sir.
Thank you. Thank you, sir. Right. I can hang up, right?
Yes, sir.
Okay. Thank you very much.
Thank you, sir. Thank you.
Thank you. Thank you, sir. Right.
Audience, please be on line. So we are going to start our validity exactly at 5 p.m. Bye, sir.
Participants can download the abstract book with the link.
Yeah.
When channel, you should not be getting confused. Certificate channel, you should. Okay, okay, okay.
Sir, Suresh, please start. This service taking.
A very good evening and a warm welcome to all of you to this valedictory session of the Virtual International Transdisciplinary Conference. Last 3 days, we have had deep insights into several fields of research. We had speakers and scholars from national and international levels enlightening us both in theory and in experimental ways to reflect philosophically on these different themes, including COVID management. Thank you very much to you all. Now I take this opportunity to invite Dr. James Jabasilan Samuel to deliver the welcome address. Please, sir.
Respected Dean, School of Advanced Sciences, the speakers, the conveners and the co-conveners, faculty members, participants, a very good evening to one and all. It's a great pleasure and honor to welcome our registrar, Dr. K. Satyanandan, for this valedictory function of Virtual International Transdisciplinary Conference 2020. I'm also happy to welcome our Dean SAS, Dr. Giuseppe, for this function. And also I request, also happy to welcome our registrar to announce the Best Oral Presentation Awards and give his valedictory address. Welcome you all.
Thank you, sir. Now I request our participants to give our feedback about the conference. Participants are requested to raise the hand so that we will call you one by one. And sir, please unmute.
Hello. Hello.
Yes, please.
Yes,
you are audible.
Yeah, this is Amrit Thakur from CG, Anna University. I would like to thank the organizer for organizing such a wonderful 3-day multidisciplinary conference. We have heard some pioneer lectures regarding energy storage, 2D material and conversion. And it was a wonderful opportunity for us to participate and learn so much from the pioneers in the field. Thank you so much.
Shalom, you can unmute and you can give your feedback.
Shalom, you raised your hand, so please go ahead.
Hello. Yes. Can you hear me?
Yes, we can hear you.
Okay, good evening all. I'm Shalaman Matthews, research scholar from VIT Vellore, and Virtual International Transdisciplinary Conference VITC was a very good experience to me. And it has been a great reminder that in spite of all the chaotic situation around us, there is still a space to share the research ideas and outputs. And it was the most interesting part of this conference was that it was multidisciplinary. So from medical science to magnetics to spintronics, to biophysics, we had a journey of sessions. So it was quite interesting. And few of my favorite topics were magnonics, cavity magnonics by Professor Maruccio, and natural language processing by Dr. Mishiko, and to the last talk given by Dr. Rajan Prabhu sir. And I would like to thank all the organizers of VITC 2020 and also the VIT management for conducting such a great, painstakingly great effort for conducting such a great conference. Thank you.
Arul, you can speak.
Good evening, sir. This is Arul from Cohost College of Technology, and it's been a great pleasure for me as an alumnus from the research group. It was a great pleasure to present my research work in front of my professors, and the arrangements done by our research group was really awesome. During this chaotic new normal situation, organizing an international conference is a big deal. So the various speakers who have given their valuable suggestions and a great gathering across the globe on various interdisciplinary approaches, especially natural language processing for the necessity of material science and other aspects, and energy storage, plasmonics, which have been a new era of research, allowing us to participate in this conference. And I hope this will be a great eye opener in the near future for the other conference also. Thank you, sir.
Thank you, participants. For want of time, participants are requested to give their feedback in the chat box. It's my privilege to invite our registrar, Dr. K. Satyanarayanan, to felicitate the virtual gathering and announce the Best Presentation Awards. Please, sir.
Good evening to all. I am very happy to participate in the valedictory function of Virtual International Transdisciplinary Conference organized by Department of Physics, School of Advanced Sciences. I am very happy to see so many participants even at the time of COVID. And during these 3 days, all the invited speakers discussed about various topics such as COVID management, crystal growth, energy harvesting, language processing in science, magnetism, supply chain management, and so on. 16 speakers from USA, Russia, UK, Italy, Germany, Japan, Australia, Turkey, and Singapore delivered lectures for the past 3 days of conference. I hope that all of you might have benefited from the presentation made by the professors and various researchers from these countries. And 652 participants were attended this conference. We have received abstracts from Algeria, Belgium, Indonesia, Japan, Nigeria, etc. Our Honorable Chancellor released the abstract book with EISBN during the inaugural function. 48 contributory papers were called for oral presentation under 4 different sessions, out of which 4 papers are selected for the Best Oral Presentation Award by 4 panel of judges. I am very happy to inform that these awards are sponsored by VB Ceramics Research Center, Chennai, and Mitutoyo South Asia Private Limited, Chennai. I thank all the invited speakers and participants who made this conference a successful one. I also appreciate the organizing committee members who actively involved in this conference during this pandemic situation. Without their cooperation and full-fledged involvement, this will not be possible. Now the important business of the thing, that is the winners of the oral presentation during VITC 2020. So I will read theme by theme and winners. First theme, COVID-19 management, drug delivery, and language processing in science. The winner is Mr. Sakti Jayasundar Rajasekhar. He is from Melmarvattur Adiparasakti Institute of Medical Sciences and Research, Melmarvattur. Second theme is crystal growth and magnetism. And the winner is Miss Shalom Ann Matthews, Vellore Institute of Technology, Vellore. And the third theme is energy harvesting and light matter interaction at atomic scale. Winner is Mervyn Vincent, IMDEA Material Institute, Madrid, Spain. And fourth and last theme is nanoelectronics, reliability in nanoelectronics, molecular engineering, and supply chain management. Winner is Mr. T.H. Vignesh Kumar, Department of Chemistry, SRM Institute of Science and Technology, Katamulathur, Tamil Nadu. So congratulations to all the winners. Thank you.
Thank you so much, sir, for your inspiring words and announcing the Best Oral Presentation Awards. Now I'm happy to invite Dr. Ramesh Tamankar to convey the vote of thanks.
Good evening, everybody. Good evening, everybody. Any event like this need a strong backup from the institution and people involved in the institution. In this regard, I sincerely thank our beloved Chancellor, Vice President, Assistant Vice President, Vice Chancellor, Pro-Vice Chancellor, and Registrar for allowing us to conduct this conference. I hope this support will always be there with us. Many thanks goes to the Dean, School of Advanced Sciences, Professor Mary Sarel, and Head of the Physics Department, Professor K. Senthilnathan, for extending their continuous support for smoothly conducting this first transdisciplinary conference in VIT Vellore. Our gratitude also goes to the Director, Event Management Team in VIT, and Assistant Director of the CTS team. Here, I would like to give a special mention to Mr. Gopi and Mrs. Shobana for their continuous support during this event. It's a well-known fact that there exists a close relation between science and technology and ultimately overall development of a nation. We have seen numerous examples in the history where nations have progressed rapidly when science and technologically important industries work together hand in hand. Science and scientific community generally do not value any geographical borders. Our conference is a prime example for this. Over the last 3 days, we have witnessed our beloved speakers speaking from countries like USA, Germany, UK, Italy, Turkey, Singapore, Japan, Russia, and Australia. What did we do for this? We just used the technology in the form of emails and phones and are successful in bringing them together so that our event became successful. So these people are like-minded who want to spread the message of science and scientific knowledge in spite of belonging to various time zones. On behalf of organizing committee and the Department of Physics and School of Advanced Sciences, I sincerely thank all the invited speakers for taking their valuable time and sharing their ideas with us. I would like to send our gratitude to all the session chairs who helped us to conduct the sessions very smoothly throughout the conference. Many thanks also goes to the judges who helped us in evaluating the oral presentations. Any conference is not complete without the active participation of the participants. We are delighted to tell you that throughout the 3 days of conference, we had about 150 to 175 participants in each session. I'm sure they would have gone back home picking up few points which they can implement in their scientific endeavor. I sincerely thank all those participants of this conference. Finally, but not least, the entire faculty team who came together to put this conference in place and working tirelessly throughout since the idea of transdisciplinary conference came up. I personally congratulate all the team members for coming with the various ideas and making them happen in timely manner. It was wonderful working with this team. Hope we will get another opportunity to work with bigger group of faculty members in future. We all acknowledge the help from the staff members of the department for helping us throughout. Hopefully, we will continue hosting this kind of conference in future, either online or face-to-face. We would love to have you all for those events also. Thank you very much.
Thank you, sir. The end of a story is the new beginning for many others. On this note, let us conclude a remarkable, memorable, and knowledgeable valedictory session. On behalf of the institution, we sincerely thank the dignitaries for being with us and enlightening us with their enthusiastic remarks. My heartfelt gratitude to the professors of physics VIT family for their wholehearted support rendered in the success of this virtual conference during this pandemic situation. Thank you very much. Have a great evening. Abstract book link has been sent to you via chat box. The QR code will be available in the website for another 1 week. Participants can download that. Certificate of participation and presentations will be communicated to you all by our organizing committee within a couple of days. Formally, we are closing the session now. Thank you and wish you good luck.